Welcome to Moonlight Mysteries, a calm space for long research-rich mysteries. If you enjoy these sleepy deep dives, please like this video, subscribe, and tap the bell so you don't miss new episodes. If you'd like to support the channel, a quick comment with your favorite moment helps more people find us. Now settle in, dim the lights, and let's begin. The Antikythera Mechanism. Introduction. Imagine for a moment that you are a sponge diver. The year is 1900. The place is the Eastern Mediterranean Sea, in waters not far from a small, wind-scraped island called Antikythera, which sits in the narrow passage between Crete and the Greek mainland. A place so remote and so buffeted by seasonal storms that even today its population numbers only in the dozens. You have been diving these waters for years, maybe your whole life. You know how the sea changes color as you descend, the brilliant turquoise near the surface giving way to a deep cathedral blue, and then, below 40 meters, a kind of blue-green twilight that feels more like dusk than ocean. You know the silence down here. You know the pressure in your ears, the slow compression of your chest, the way your heartbeat slows as you drift toward the seafloor. You know the feeling of the cold coming up from the dark water beneath you. The dark that begins around 50 meters and goes down and down without end. On this particular morning in the spring of 1900, a diver named Elias Stadiatis descends along a rocky underwater cliff and finds something that has no right to be there. Scattered across the sandy floor in the dim light are shapes, the curves of marble and bronze, the unmistakable lines of human figures, arms and torsos, and faces frozen in attitudes of grace and anguish. A horse, a hand reaching upward, the green corroded bulk of something enormous lying half buried in the sediment. There's a ship down here, or what used to be a ship, and it is enormous. And it has been here for a very long time. The cargo it carried sank 2,000 years ago and stayed there, patient as a stone, waiting in the dark water until this quiet morning when a man in a weighted suit with a single lungful of air found it by accident while sheltering from a storm. Stadiatis surfaced and told the captain, Demetrios Kontos, what he had seen. Kontos went down himself and came up holding a bronze arm. They knew immediately that this was something extraordinary. They returned to their home island of Simi, and then to the authorities, and within months, the Greek government had organized a formal salvage operation with the Hellenic Royal Navy providing surface support while the Simi divers did the underground work. The Simi divers were consummate professionals, the best in the world at what they did. Simi is a small island just north of Rhodes, and for centuries, its population had made their living diving for sponges in the deep waters of the Aegean and Eastern Mediterranean. They used no breathing apparatus. They dove on a single lungful of air, wearing weighted suits to help them descend quickly. And they worked at depths that would have impressed even modern recreational divers. The physical demands were extraordinary. Repeated descents to 45 meters, working in near darkness in cold water with no communication with the surface, hauling heavy objects by hand. Several divers suffered the bends, decompression sickness, from ascending too quickly. The work went on for months. Over that time, they brought up a remarkable collection of objects, bronze statues, including the famous Antikythera Mechanism, a nearly life-size bronze figure of a young man, probably Hercules or Perseus, now dated to around 340 to 330 BCE, and considered one of the finest surviving examples of ancient Greek bronze sculpture. There were also marble figures, ornamental furnitures with bronze fittings, glasswares of extraordinary quality from the workshops of the Eastern Mediterranean, ribbed bowls, blown vessels, mosaic glass, silver and gold jewelry, ceramic amphorae, dozens of them still sealed with their ancient contents of wine and olive oil and fish sauce. Coins. The ship itself, which later estimates put at over 50 meters in length, enormous for the ancient world, a vessel capable of carrying hundreds of tons of cargo across the open Mediterranean. It was, by any measure, one of the greatest archaeological finds in history. The ship has been called the Titanic of antiquity, not because of the drama of its sinking, though a storm in that treacherous passage certainly qualifies, but because of the richness of what it carried and the completeness with which the seafloor preserved it. Nothing like it had been found before, and very like it has since been found. But among all the treasures, one object would prove to be the most extraordinary find in the history of science and technology. It did not look like much at first. It did not look like much at all. It was a corroded lump of bronze and wood, barnacled and greenish black, crumbling at the edges, roughly the size of a thick hardcover book. Later measurements would establish its original dimensions as approximately 34 centimeters tall, 18 centimeters wide, and 9 centimeters deep. It was heavy in the way that solid metal is heavy, with a density and presence that did not match its size. It looked, in the underwater darkness, like nothing. It looked like the kind of thing you would set aside while you dealt with the statues. This was the Antikythera Mechanism. What it actually was, what it contained inside that corroded shell, what it had been designed to do, what tradition of human knowledge and craft it represented, would take more than a century to fully understand, and what researchers eventually found inside would force a complete rewriting of history of human technological achievement. Inside that lump of corroded bronze, preserved by the particular chemistry of the Aegean seafloor, was a mechanical computer, a working, geared, hand-operated astronomical calculator of breathtaking sophistication, capable of modeling the motions of the sun, the moon, and all 5 planets visible to the naked eye, simultaneously from a single hand-cranked input. It would predict solar and lunar eclipse decades into the future, accounting for the complex interactions of multiple overlapping astronomical cycles. It tracked the Egyptian solar calendar and the Greek lunar calendar simultaneously. It displayed the dates of the ancient Olympic Games and the other great pan-Hellenic festivals. It encoded the mathematics of Babylonian astronomy alongside the geometry of ancient Greece. And it did all of this in a package small enough to carry under one arm. It was built roughly 2,000 years before anything of comparable mechanical sophistication would appear again in human history. The Antikythera Mechanism is the oldest analog computer ever found. It is a singular object. There is nothing else like it from antiquity, no second example, no near contemporary rival. And the longer researchers have studied it, the more it has revealed, not just about the device itself, but about the extraordinary minds that created it, the world they inhabited, the vast tradition of astronomical knowledge that made it possible, and, perhaps most intriguingly, the deep, unsettling questions it raises about what we think we know about the ancient world, about the nature of technological progress, and about how much human brilliance has simply vanished from the record without leaving a trace. This is the story of that object. All of it. The science, the scholarship, the history, the people, the long decades of difficult research, and the wonderfully strange ideas at the edges of the map, where the territory of the known gives way to the open water of speculation and wonder. Because the Antikythera Mechanism is, among other things, a machine for generating awe. And awe, in the end, is the whole point. Chapter 1. The World That Made the Mechanism. The Eastern Mediterranean in the Hellenistic Age. To understand the Antikythera Mechanism, you have to understand the world that produced it. In that world, the Hellenistic Greek world of the 2nd and 1st centuries BCE, was one of the most intellectually fertile environments in all of human history. Something was happening in the Eastern Mediterranean in those centuries, something extraordinary and unrepeated, and the Antikythera Mechanism is one of its most tangible surviving products. The Hellenistic period is generally dated from the death of Alexander the Great in 323 BCE to the Battle of Actium in 31 BCE, when the Octavian's forces defeated Cleopatra and Mark Antony in Rome, absorbed the last major Hellenistic kingdom, Egypt. These roughly 3 centuries saw an extraordinary flowering of science, mathematics, philosophy, and technology across the Greek-speaking world, a world that now stretched, thanks to Alexander's conquests, from Greece and Egypt in the west, all the way to the borders of India in the east. This was the era of Euclid, who systemized geometry into the form we still largely teach today, whose elements remain the standard textbook of mathematics for 2,000 years. It was the era of Archimedes of Syracuse, who calculated increasingly accurate approximations of pi using a method of exhaustion that was genuine precursor to calculus, who worked out the mathematics of spirals and parabolas and spheres, who proved that the volume of a sphere is 2/3 the volume of the circumscribing cylinder, and was so delighted by this result that he reportedly asked for a sphere inside a cylinder to be inscribed on his tomb. It was the era of Eratosthenes of Cyrene, who served as head of the Library of Alexandria and calculated the circumference of the earth to within perhaps 2% of the modern value by measuring the angle of the sun's shadow at 2 locations a known distance apart, a feat of geometric reasoning so elegant that it still takes the breath away. It was the era of Apollonius of Perga, who cataloged the conic sections, the ellipse, the parabola, the hyperbola, with such completeness that his work remained authoritative for 18 centuries. And it was the era of Hipparchus of Nicaea, who compiled the first star catalogue, discovered the precession of the equinoxes, and created detailed mathematical models of the moon's motion that were not substantially improved upon until Kepler. What distinguished this period was not just the quality of its individual thinkers, brilliant as they were. It was the quality of the conversation between them, the density and intensity of intellectual exchange across a wide and surprisingly well-connected world. Letters traveled, scholars moved between cities, books were copied and distributed. The great libraries collected not just local knowledge, but everything they could acquire from everywhere. When Archimedes in Syracuse wanted to share a mathematical discovery with a colleague in Alexandria, he could write a letter that would arrive in a matter of weeks. When a new astronomical observation was made in Rhodes, the news could reach Babylon in Egypt and Athens within a season. This connectivity enabled something unprecedented: the systematic accumulation and synthesis of knowledge across different cultural traditions. And it is this synthesis, particularly the synthesis of Greek geometric reasoning with Babylonian observational astronomy, that made the Antikythera Mechanism possible. The island of Rhodes. Rhodes deserves a special attention in any account of the Antikythera Mechanism, because the evidence, taken as a whole, points with some insistence towards this small island as the place where the device was made. The island of Rhodes sits at the southeastern corner of the Aegean Sea, close to the coast of what is now Turkey. It is not large, roughly 80 kilometers long and 40 kilometers wide, but its position made it one of the most important trading and cultural hubs in the ancient Mediterranean. Ships traveling between the eastern Mediterranean, the Levant, Egypt, the Black Sea, and the western Mediterranean, Italy, Sicily, North Africa, pass through Rhodian waters almost inevitably. The island's magnificent harbor, its skilled sailors, and its sophisticated legal and commercial traditions made it wealthy. And its wealth supported a culture of unusual intellectual sophistication. By the 2nd and 1st century BCE, Rhodes had become one of the most important centers of scientific and philosophical thought in the Greek world. It was home to an important school of Stoic philosophy. It had traditions of both practical engineering and theoretical science. It was where Hipparchus, the greatest astronomer of antiquity, spent most of his working life. And it was, according to the Roman writer Cicero and other sources, the origin of at least one mechanical astronomical device similar to the Antikythera Mechanism. The evidence connecting the mechanism specifically to Rhodes is multiple and mutually reinforcing. The dialect of Greek used in the mechanism's inscriptions is consistent with the Rhodian dialect of the 1st century BCE. The astronomical star calendar on the front of the device, the parapegma, works best for latitudes between 33.3 and 37 degrees north, which corresponds to the latitude of Rhodes, 35.85 to 36.5 degrees north. The game dials on the back of the mechanism includes the Haliea, a major festival of athletic games held specifically on Rhodes, and the Na Games at Dodona. The cargo amphorae found on the shipwreck are of the mathematical traditions it draws on, corresponds closely to what we know about the scientific work being done at Rhodes in the late 2nd and early 1st century BCE. None of this is individually conclusive, but taken together, it builds a fairly strong circumstantial case. The most careful scholarly assessment, published by researcher Paul Iverson in 2017, concluded that the prototype for the device was indeed from Rhodes, but that this particular copy may have been modified for a client from Epirus in northwestern Greece, someone who wanted the same device but with a calendar adjusted to their local festival cycle. Hipparchus of Nicaea. Of all the figures who may have contributed to the Antikythera Mechanism, none casts a longer shadow than Hipparchus of Nicaea. Understanding Hipparchus is essential to understanding the mechanism, because, in a very real sense, the device is his astronomy made physical, his mathematics translated into bronze. Hipparchus was born sometime around 190 BCE in Nicaea, a city in the region of Bithynia, in what is now northwestern Turkey. We know almost nothing about his early life or education. At some point, he moved to Rhodes, where he spent most of his productive years. He is generally dated to the period between about 190 and 120 BCE, which would make him a younger contemporary of Apollonius of Perga. He may have spent time in Alexandria. The great observatory there would have given him access to records and instruments unavailable elsewhere. He died sometimes after 127 BCE, the date of his last recorded observation. None of Hipparchus's original works have survived intact. We know of his achievements primarily through the writings of later authors, most importantly Ptolemy of Alexandria, who wrote his great astronomical synthesis, the Almagest, around 150 CE, and acknowledged Hipparchus as his most important predecessor. This is a double-edged inheritance. Ptolemy preserved and credited Hipparchus's work, but he also superseded it, with the result that later generations studied Ptolemy rather than the original, and the original was eventually lost. Despite the fragmentary nature of the evidence, the picture of Hipparchus's achievements that emerges from later sources is staggering. He compiled the first comprehensive star catalog in the Western astronomical tradition, recording the positions and apparent brightnesses of over 1,000 stars. The catalog was precise enough that he could compare his star positions with those recorded by earlier Greek astronomers, particularly Timacharis and Aristillus, working in Alexandria a century before him. When he made his comparison, he noticed something remarkable. The stars had all shifted systematically by the same amount and the same direction. Not by a lot, only about 2 degrees over a century. But the shift was consistent and undeniable. The stars were moving, or rather, the Earth's axis was wobbling, slowly, like a spinning top beginning to precess. The equinoxes, the points at which the sun crosses the celestial equator in spring and autumn, were creeping backward through the zodiac at a rate of about 1 degree every 72 years. Hipparchus had discovered the precession of the equinoxes, one of the most important phenomena in observational astronomy, with implications for calendar making and celestial navigation that would resonate for millennia. He made precise measurements of the distance and size of the moon using geometric methods, specifically by observing the geometry of solar eclipses as seen from different locations. His value for the distance to the moon, expressed in Earth radii, was reasonably accurate. He determined the length of the synodic month, the time from one new moon to the next, to within 1 second of the modern value. This is an astonishing achievement for naked eye observation in the 2nd century BCE. Most relevant to the Antikythera Mechanism was his work on the moon's irregular motion. The moon does not orbit the Earth in a perfect circle at a constant speed. It follows an elliptical path, which means it moves faster when it is closer to Earth and slower when it is farther. The difference in speed is noticeable. The moon can be moving nearly 15% faster, and it creates a pattern of variable motion across the sky that is complex enough to require a genuine mathematical model. Hipparchus developed 2 equivalent ways of modeling this variable motion: the eccentric model, in which the moon orbits in a circle whose center is offset from the center of the Earth, and the epicyclic model, in which the moon moves in a small circle, the epicycle, whose center itself moves in a larger circle, the different, centered on Earth. Both models produced the same observational predictions, and both were known to Hipparchus. The pin and slot mechanism in the Antikythera Mechanism is a direct mechanical realization of the epicyclic model. The offset axis of the K-gears produces precisely the sinusoidal variation in speed that Hipparchus's theory described. There is something haunting about this connection. Hipparchus worked at Rhodes sometime in the 2nd century BCE. The mechanism's moon mechanics encodes his theory with extraordinary fidelity. The ship carrying the mechanism was probably coming from Rhodes. The inscriptions used the Rhodian dialect. The game style includes Rhodes' own festival. The weight of circumstantial evidence suggests that whoever built the mechanism was working in the same intellectual community where Hipparchus worked, possibly within a generation of his death, possibly with direct access to his records and methods. Whether Hipparchus himself contributed to the design, or whether a craftsman in his circle did, or whether someone working from his written texts did, we cannot say. But his ghost is in every gear. Posidonius in Cicero's Witness. Another figure worth dwelling on is Posidonius of Apamea, because he gives us something invaluable, a contemporary human witness to the existence of devices like the Antikythera Mechanism. Posidonius was born around 135 BCE in Apamea, a city in what is now Syria. He was a Stoic philosopher of the first rank, but also an extraordinarily wide-ranging scholar who wrote on geography, history, meteorology, physics, astronomy, mathematics, and the natural world. His works, unfortunately, survive only in fragments quoted by later authors, but those fragments reveal a mind of remarkable scope and ambition. He traveled extensively to Spain, to Gaul, to North Africa, observing ocean tides, the behavior of stars near the horizon, the custom of different peoples. He settled eventually on Rhodes, where he founded a school that became one of the intellectual centers of the Hellenistic world. The Roman orator and statesman Cicero studied under Posidonius on Rhodes between 79 and 77 BCE. He was impressed. Cicero later wrote about a mechanical device that Posidonius had made, a bronze model that reproduced the motion of the sun, moon, and 5 planets. He described it with wonder and with a characteristic philosophical flourish. If you took such a device to the distant north, to the Scythian or Britons, even those barbarians would recognize from its ordered motions that it must have been made by a rational intelligence. The cosmos, Cicero was arguing, is like this device, too orderly to be the product of chance, too precise to be anything but the work of a designing mind. This description is tantalizing. Posidonius's device sounds very much like what the Antikythera Mechanism was designed to do. It was not a simple sphere showing constellations. It was a model of planetary motions, a working orrery of some kind. Was Cicero describing the Antikythera Mechanism itself? Almost certainly not. The shipwreck dates to about 70 to 60 BCE, which is after Cicero's visit to Rhodes. But was he describing something essentially similar? Almost certainly yes. Posidonius's device and the Antikythera Mechanism appear to be representatives of the same tradition, a tradition of precision mechanical astronomical modeling that flourished at Rhodes in the 1st century BCE. The Babylonian Foundation. To fully understand the Antikythera Mechanism, you have to go back further than Greece, further than the Hellenistic period, further even than the Persian Empire that Alexander destroyed. You have to go back to Babylon, into a tradition of astronomical observation that is among the oldest and most sustained in human history. The Babylonians, or more precisely, the succession of cultures that occupied the Tigris-Euphrates River Valley over more than 2 millennia, from the Sumerians and the Akkadians through to the Chaldeans, had been systematically watching the sky and recording what they saw for a very long time. Their observations were motivated partly by religion. Celestial events were interpreted as divine communications, as omens of earthly events, and partly by practical necessity. Agriculture requires a reliable calendar. Navigation requires knowledge of the stars, and partly by something that looks, across the millennia, like pure scientific curiosity. Their records, preserved on clay tablets in cuneiform script, accumulated over centuries into an archive of astronomical data of unparalleled depth. By the time Alexander's armies arrived in Mesopotamia, the Babylonian astronomical archive contained hundreds of years of systematic observations of the moon, the sun, the 5 naked-eyed planets, and eclipses, records going back in some cases to the 8th century BCE and beyond. What the Babylonians developed from this data was not a geometric model of the solar system. They did not ask, in the way that Greek philosophers did, what physical arrangement of spheres or circles could account for what they observed. Instead, they developed what we would now call an algorithmic or arithmetic approach. They noticed patterns in their data, regularities, cycles, recurrences, and they found mathematical formulas for predicting future events based on those patterns. Their approach was fundamentally numerical, rather than geometric, and it was extraordinarily effective. The Babylonians discovered, or more precisely recognized from their records, a series of astronomical period relations of remarkable precision. The most important of these for the Antikythera Mechanism are the following. The Metonic cycle. 235 lunar months is almost exactly equal to 19 solar years. The correspondence is astonishingly close. After 19 years, the moon returns to very nearly the same position in the sky relative to the sun on very nearly the same calendar date. The discrepancy is only about 2 hours over the entire 19-year period. This cycle is invaluable for calendar makers because it provides a systematic way to reconcile a lunar calendar based on the phases of the moon with a solar calendar based on the seasons. The Babylonians had known this cycle for centuries before the Greek astronomer Meton of Athens introduced it to the Greek world around 432 BCE, and before it was encoded in the upper back dial of the Antikythera Mechanism. The sorrow cycle, 223 lunar months, approximately 18 years and 11 days, is the fundamental eclipse prediction cycle. After one sorrow's period, the sun, moon, and earth return to very nearly the same geometric relationship, and so the pattern of eclipses begins to repeat. If a solar eclipse occurs today, a similar one will occur one sorrows later, though not necessarily visible from the same location. The Babylonians had identified this cycle, and it forms the basis of the lower back dial of the Antikythera Mechanism. The spiral eclipse prediction dial, with 223 cells, one for each month of the cycle, with glyphs indicating the likelihood and type of any eclipse. The Callippic cycle, 4 metonic cycles, or 76 years, was a refinement that provided an even more accurate reconciliation of the lunar and solar calendars. The Exalemos, or triple sorrows, 54 years, corrected for the fractional day offset that accumulated in successive sorrows periods. Both of these secondary cycles appear in subsidiary dials on the Antikythera Mechanism, the planetary synodic periods. The Babylonians had measured with considerable accuracy the synodic periods of all 5 naked eye planets, the time each planet takes to return to the same position relative to the sun as seen from Earth. For Venus, this is approximately 584 days. For Saturn, approximately 378 days. They had found period relations expressing these synodic periods in terms of whole numbers of years. For instance, that 5 synodic cycles of Venus correspond almost exactly to 8 years, or that 57 synodic cycles of Jupiter correspond to 59 years. These period relations are what the Antikythera Mechanism's gear trains for the planets are designed to embody. What happened when Greek science encountered this Babylonian tradition was one of the most productive intellectual collisions in history. The Greeks had something the Babylonians lacked, a powerful tradition of geometric modeling, a desire to understand the physical structure of the cosmos rather than merely predict its observable events. The Babylonians had something the Greeks lacked, centuries of meticulous observational data and a set of extremely accurate numerical period relations derived from the data. The synthesis of these two traditions, the Greek geometric models using Babylonian period data, produced the astronomy of Hipparchus, of Apollonius, of Geminus, and ultimately of the Antikythera Mechanism. The technology of gears. Before the Antikythera Mechanism was found, historians of technology generally believed that complex geared machinery was a medieval invention. The mechanical clock, with its intricate gear trains, escapements, and astronomical displays, was considered a product of the 14th century CE. gear devices of any kind were thought to have been unknown or extremely primitive in the ancient world. The discovery and analysis of the mechanism changed this assumption completely, and it is worth spending some time on the mechanics of gears themselves, on what they are, what they can do, and why the mechanism represents such an extraordinary achievement. A gear is, at its most basic, a wheel with teeth cut around its rim. When the teeth of two gears mesh together, the rotation of one wheel is transmitted to the other. This is the fundamental operation, the transfer of rotational motion from one shaft to another. But the power of gears comes from what happens when the two meshing wheels have different numbers of teeth. If gear A has 60 teeth and gear B has 20 teeth, then for every complete rotation of A, gear B rotates 3 times. The ratio of rotation speeds is inversely proportional to the ratio of tooth counts. This is the gear ratio, and it is the key to everything the Antikythera mechanism does. By chaining together sequences of meshing gears, what engineers call gear trains, you can produce extraordinarily complex transformations. A single input rotation applied to the first gear in a train can produce a dozen different output rotations at different speeds from the other gears in the train. And if you design your gear tooth counts carefully, you can choose exactly the right number of teeth for each gear. You can make each output rotation correspond to a specific astronomical period. You can make one shaft rotate once in exactly one sidereal year. Another shaft can rotate once in one sidonic month. Another can complete one revolution in exactly 18.61 years, the period of the moon's nodal cycle relevant to eclipse prediction. Each gear ratio is a ratio of astronomical periods, encoded in the ratio of tooth counts. This is what the Antikythera mechanism does. Its gear trains are not arbitrary assemblages of mechanical components. They are mathematical statements about the structure of the solar system, expressed in the language of tooth counts and meshing ratios. To read the gears of the mechanism is to read an astronomical textbook written in bronze. The precision required to make this work is extraordinary, and it cannot be overstated. Each gear must have exactly the right number of teeth, not approximately right, but exactly. A gear with 223 teeth and a gear with 224 teeth will produce completely different outputs. There's no such thing as close enough in a gear train designed to model astronomical periods over decades. Furthermore, the teeth must be cut to consistent size and spacing, or adjacent gears will bind, skip, or fail to mesh properly. The gears must fit together in exactly the right spatial arrangement. The shafts must turn freely in their bearings without excessive play. All of this must work together simultaneously, reliably, over a period of years. How ancient craftsmen achieved this precision is one of the most fascinating open questions in the history of technology. They had no lathes in the modern sense, no milling machines, no computer-controlled cutting tools. They worked with hand tools, drills, files, gravers, saws, and with whatever geometric dividing techniques they had developed. Some researchers have proposed that they used a dividing plate, a flat disc with precisely spaced holes used to guide the cutting of gear teeth, similar in principle to the dividing heads used in modern machine shops. The machinist Chris Budasilic spent years recreating the mechanism using only ancient tools and techniques, and his project revealed both the feasibility of the ancient methods and the extraordinary skill required to execute them. The gears of the Antikythera mechanism are cut with triangular teeth. Each tooth is an equilateral triangle in cross-section. This is not the optimal tooth profile by modern engineering standards, which prefers the involute curve for its superior load-bearing and meshing properties. But it is internally consistent, it works, and importantly, it is geometrically simple, which makes it easier to cut accurately by hand. The choice of triangular teeth may reflect a deliberate decision to prioritize manufacturability over load-bearing capacity, which makes sense for a device that transmits very little torque. It is driven by a human hand, after all, but demands very precise and consistent tooth spacing. The bronze alloy used for the gears is another choice worth noting. Bronze, an alloy of copper and tin, with the specific composition varying by application, was the workhorse metal of the ancient world. It is harder than pure copper, casts and machines well, and resists corrosion better than iron. The choice of bronze for the mechanism's gears was almost certainly deliberate. It is the material that allows both the precision machining of gear teeth and the long-term durability of the device. That same bronze, now 2,000 years old and heavily corroded, is what allowed the mechanism to survive at the bottom of the sea. A wooden mechanism would have rotted away within decades. An iron mechanism might have rusted to nothing. The bronze corroded, yes, but it corroded slowly, and the corrosion products themselves formed a hard protective crust that encased the gears and preserved their shape, imperfectly but sufficiently for 2 millennia. Chapter 2. The Ship and the Sea. What the ship was carrying and why. The ship that carried the Antikythera mechanism to its resting place was no ordinary merchant vessel, and its cargo was no ordinary cargo. It was a large Roman-era ship, estimated at over 50 meters in length, loaded with an astonishing concentration of fine art and luxurious goods from the Greek world. Bronze statues, marble sculptures, fine glassware, gold and silver jewelry, sealed amphorae of wine and oil, the kind of cargo that would have been worth a fortune in Rome, the kind of cargo that people went to war over. The dating of the wreck to somewhere between 70 and 60 BCE places it in one of the most turbulent periods of late Republican Rome. This was the era of Julius Caesar's early career, of the military campaigns of Pompey, of the Roman Republic's slow collapse into civil war. Roman generals were systematically stripping the Greek world of its finest art, not secretly but openly, as the legitimate spoils of conquest and governance. Lucius Cornelius Sulla had sacked Athens in 86 BCE and carried off enormous quantities of art. Gaius Verus notoriously plundered Sicily in the 70s BCE. The traffic in looted Greek art flowing toward Rome in this period was substantial and well documented. The most plausible theory about the Antikythera ship is that it was carrying looted or purchased treasure from Greek East toward Rome, probably to adorn a triumphal parade or the houses of wealthy Romans. Julius Caesar was indeed planning a great triumph in this period, and some researchers have suggested that the Antikythera cargo may have been destined for his celebrations, though this is speculative. The second theory is that the mechanism specifically was a diplomatic gift or a luxury purchase, transported as an expensive curiosity for a wealthy Roman patron, someone like Cicero's friend Atticus, who had a taste for Greek scientific instruments, or perhaps Cicero himself. We know from a 2016 expedition to the wreck site that at least one young person died on this ship. A skeleton, apparently male, was found in the wreckage. Jacques Cousteau's famous 1976 expedition found 4 sets of human remains. These were real people with lives and families and destination who did not survive the storm that caught them in the passage between Antikythera and Crete, sometimes around 60 years before the Common Era. The mechanism they were carrying did not reach its intended recipient. The recovery and identification. The salvage operation of 1900 to 1901 was the first major underwater archaeological excavation in history, though this was not fully recognized at the time. The semi divers worked without any of the tools and techniques that modern underwater archaeology takes for granted. No airlift to remove sediment, no underwater cameras, no systematic grid survey of the site. They worked by feel, in near darkness, grabbing what they could and hauling it to the surface. The miracle is not that some things were missed or damaged in the process. The miracle is that anything survived at all. The corroded lumps of bronze that would become the mechanism arrived at the National Archaeological Museum in Athens unremarked. They were cataloged, numbered, and stored, while the more obviously spectacular finds, the statues, the glassware, the jewelry, received attention and conservation treatment. The bronze lump were interesting and unusual, but they were not immediately comprehensible as anything in particular. Then, on May 17, 1902, a date now celebrated annually, marked with a Google Doodle in 2017, commemorated in museums and classrooms around the world, an archaeologist named Valerio Steas was examining the fragments when he noticed something in a piece that had cracked or split during recovery or storage. There, visible in the fractured surface, were the teeth of a gear wheel, perfectly formed, evenly spaced, unmistakable. Steas was astonished. He knew that gear wheels had no place in the archaeological record of ancient Greece. He proposed immediately that the object was an astronomical clock or calendar of some kind, and he was right in essentially every respect, though it would take a century in a succession of increasingly powerful analytics technology to understand just how right he was. His colleagues were not ready to believe him. The device was too sophisticated, too complex, too far outside the expected capabilities of ancient craftsmen. The most common objective was that it must be a medieval astrolabe, an Islamic or Byzantine instrument somehow mixed in with the ancient cargo. This objection had the virtue of being wrong in a consistent and specific way. Medieval astrolabe, beautiful as they are vastly simpler than the Antikythera mechanism. They do not contain differential gear trains or epicyclic mechanisms, or multiple interlocking pointers. But this was not obvious to scholars who had not yet examined the mechanism carefully. The first person to take the object seriously as a genuine ancient artifact and to correctly characterize its likely function was a German philologist named Albert Riem, who examined it carefully in the early 1900s and proposed in his notes that it was an astronomical calculating machine. Ream's analysis was remarkably perceptive for its time, but he never published a full account of his findings, and his manuscript notes sat in a library archive for decades, largely unknown to the scholars who might have benefited from them. The mechanism sat in its museum case, and the world moved on. Chapter 3: The Long Road to Understanding. Derek de Sola Price, the man who unlocked the machine. The silence around the Antikythera mechanism lasted nearly 50 years after Seuss's identification. There were occasional references, occasional speculations, occasional visitors to the museum who noted its existence and moved on. No sustained program of research, no serious attempt to understand the device in its totality. Then, in 1951, an English physicist named Derek J. de Sola Price walked into the National Archaeological Museum in Athens, saw the mechanism, and was not able to walk away from it. Price was an unusual figure, a physicist by training who had become one of the founders of the academic discipline of the history of science. He combined rigorous quantitative thinking — he would later invent scientometrics, the statistical study of scientific publications — with a deep humanistic interest in how knowledge was created and transmitted across time. He had published on the history of scientific instruments. He understood gears. He understood ancient astronomy. And when he looked at the Antikythera mechanism, he understood, perhaps more immediately than anyone before him, that he was looking at something that rewrote the history of technology. Price spent 20 years on the mechanism. He visited Athens repeatedly, studied the fragments, corresponded with other scholars, built physical models to test his ideas about how the gears fit together. In 1971, he partnered with Charalampos Karakalos, a Greek nuclear physicist, to take X-ray and gamma-ray images of all 82 fragments. This was a genuine technological breakthrough. The fragments, by this point, heavily encrusted with mineral deposits and products of corrosion, were essentially opaque to visual examination. The gears and structural details inside the fragments were invisible to the eye. The X-ray images, the first ever taken of the mechanism, showed the interior in outline, the shapes and approximate arrangement of the gears hidden inside the corroded mass. Price published his analysis in 1974 in a paper titled Gears from the Greeks, the Antikythera Mechanism, a calendar computer from circa 80 BC. The paper, later expanded into a monograph, was a landmark in the history of science. Price argued that the mechanism was an ancient Greek mechanical calculator containing at least 30 interlocking bronze gear wheels, used to calculate the motions of the moon and sun through the zodiac and to predict eclipses. He proposed a construction date around 87 BCE. He compared it explicitly to a modern analog computer, a remarkable insight that has held up entirely. He argued with great force and conviction that it was evidence of a lost tradition of ancient Greek mechanical astronomy, that the mechanism was not a freak accident of history, but a representative of a whole class of devices that once existed and had been entirely lost. Price's analysis was groundbreaking, but it was also incomplete, in some respects incorrect. The X-ray technology of the 1970s, while transformative, could not resolve fine details smaller than a few millimeters. Price miscounted teeth on several gears. He misidentified some gear connections. His proposed reconstruction of the mechanism's overall layout was only partially accurate. His date estimate of 87 BCE is now thought to be too late by some researchers and approximately right by others. These limitations were not failures on Price's part. They were the natural limits of the technology available to him. But they meant that his reconstruction, for all its brilliance, left much of the mechanism still mysterious. From Price to CT, 1980s and 1990s. Price's paper catalyzed a generation of new researchers. Through the 1980s and 1990s, several groups took up the challenge of understanding the mechanism with improved methods and fresh eyes. Alan Bromley, an Australian computer scientist at the University of Sydney, worked with London clockmaker Frank Percival to create a physical working replica of the mechanism based on Price's analysis. The process of trying to actually build a working version of the device, of translating Price's theoretical analysis into physical metal components that meshed and turned, was enormously productive. It forced a level of attention to mechanical detail that no amount of theoretical analysis could replicate. When you try to make gear mesh, you discover very quickly whether your tooth counts are right. Bromley found and corrected several of Price's errors in the process of building his replica. Michael Wright, a curator and engineer at the Science Museum in London, devoted years of his professional life to the mechanism and produced some of the most important pre-CT work on the device. Working with Bromley and using a more advanced imaging technique called linear tomography, which produced cross-sectional images of the fragments, Wright identified gears that Price had missed, corrected more errors in the tooth counts, and developed a new understanding of the overall structure of the device. Crucially, Wright proposed that the front face of the mechanism had originally displayed not just the sun and moon, but all 5 naked-eye planets, a hypothesis that was controversial at the time, but that later CT research would confirm in detail. Wright built a detailed physical replica embodying his revised understanding, which demonstrated the mechanical plausibility of his reconstruction. He also identified the use of a differential gear in the mechanism, a device for adding or subtracting 2 rotations, previously believed to have been invented in the 16th century CE. The work of Bromley and Wright in the 1980s and 1990s substantially advanced understanding of the mechanism's mechanical structure and function. But there remained a fundamental limitation. The imaging technology available, however improved over Price's era, still could not resolve the finest mechanical details inside the fragments, and could not read the inscriptions hidden beneath the corrosion. The full text of the mechanism's instruction manual, the thousands of characters of ancient Greek inscribed on its internal surfaces, remained completely inaccessible. The 2005 Revolution. The breakthrough came in 2005, when an international research consortium, the Antikythera Mechanism Research Project, applied a new imaging technology to the fragments, microfocus X-ray computed tomography, or X-ray CT. CT scanning works by taking a series of X-ray images of an object from many different angles and then using computer algorithms to reconstruct a three-dimensional model of the object's interior from those images. Medical CT scanners, which most people have encountered, or at least heard of, use this principle. But medical scanners are designed for soft tissues inside a living body, and their resolution, typically on the order of a millimeter, is far too coarse for the fine mechanical and inscriptional details of the Antikythera mechanism. The machine brought to Athens for this project was a micro-focus X-ray CT scanner, capable of resolving features as small as 0.3 millimeters. This is about the width of a human hair. And at this resolution, for the first time, every gear tooth, every axle, every bearing surface inside the fragments could be seen in 3 dimensions. The researchers could virtually open the fragments on a computer screen, peel away the layers of corrosion, and examine each gear as if it had just come from the workshop. More astonishing than the mechanical details, however, were the inscriptions. The CT scans revealed text, thousands of tiny characters of ancient Greek inscribed on the interior surfaces of the mechanism, surfaces that had been sealed inside the corroded fragments for 2,000 years. These inscriptions were not just decorative or ceremonial, they were functional. They were an instruction manual. The mechanism had been covered inside and out with explanatory text. On the outer surfaces of the front and back covers, longer text described the planets and their motions and explained the overall function of the device. On the interior surfaces of the backplate, detailed instructions for using the eclipse prediction dial. On other surfaces, further explanatory notes. Complementary imaging technology, polynomial texture mapping, which uses multiple images taken from different angles under different lighting conditions to reveal surface texture invisible under normal illumination, helped read letters that the CT alone could not fully resolve. In total, the CT and PTM imaging revealed approximately 3,000 characters of ancient Greek texts inscribed on the mechanism, more than doubling the amount of inscriptional content previously known. Not all of it is fully legible. Some characters are too damaged, some too corroded, but the decipherment of this text has transformed understanding of the device and continues to yield new findings as analysis techniques improve. The results of the 2005 imaging campaign were published in a major paper in Nature in November of 2006, authored by a large international team and accompanied by widespread media coverage. For most people, both within the scholarly community and in the general public, this paper was their first real introduction to the Antikythera mechanism, and the picture it presented was electrifying. The 2016 inscriptions. One of the most remarkable discoveries in the ongoing analysis of the mechanism's inscriptions came in 2016, when researchers working through the text of what is called the front cover inscription, the inscriptional text on the outer surface of the front cover of the device, found 2 numbers that had not previously been recognized, 462 and 442. These numbers appeared in sections of the inscription dealing with Venus and Saturn respectively. At first, their significance was not immediately clear, but when researchers analyzed them in the context of astronomical period relations, as potential numbers of years corresponding to numbers of planetary synodic cycles, they revealed something remarkable. For Venus, 289 synodic cycles of Venus correspond to 462 years. This is a highly accurate period relation for Venus, far more accurate than the simple 5 cycles in 8-year relation that had previously been assumed to underlie the Venus gear train. The accuracy is only about 0.003% off from the true synodic period of Venus. For Saturn, 427 synodic cycles of Saturn correspond to 442 years. Again, this is a much more accurate period relation than had previously been assumed. What made these discoveries particularly exciting was not just the accuracy, but a subtle mathematical property. Both 462 and 442 factor into small primes. 462 is equal to 2 times 3 times 7 times 11. 442 is equal to 2 times 13 times 17. Gear tooth counts must be whole numbers. In a gear with large prime numbers of teeth, a gear with, say, 289 teeth is practically impossible to manufacture at the scale required for the mechanism. But a gear with 462 teeth or 442 teeth can be broken down into smaller gears whose tooth counts include the prime factors, and these can be manufactured with modest effort. The implication is profound. The mechanism's designers did not simply use whatever astronomical period relations were available to them. They specifically sought out period relations that were both astronomically accurate, mechanically realizable. Period relations whose numbers were factorizable into primes small enough to be expressed in gear teeth of manageable sizes. This is a sophisticated engineering optimization, requiring simultaneous mastery of astronomy, number theory, and mechanical design. It reveals a level of mathematical sophistication in the mechanism's designers that earlier analyses had not appreciated. This discovery also changed the nature of previous reconstructions. The 2021 UCL reconstruction, the most complete to date, was built directly on the foundation of these newly recognized period relations for Venus and Saturn, combined with newly recognized relations for the other planets that emerged from the ongoing inscription analysis. The 2021 UCL reconstruction. In March 2021, a team at University College London, led by Tony Freeth, published what is currently the most complete and comprehensive proposed reconstruction of the entire Antikythera mechanism in a paper in Scientific Reports. This reconstruction, for the first time, included a fully worked out mechanical model of the planetary display on the front face of the device. Previous reconstructions had been able to account for the back of the mechanism in considerable detail. The metonic dial, the Saros dial, the subsidiary dials for games and exoligmos. But the front face beyond the sun and the moon have remained mysterious. The inscriptions refer to planetary motions. The incomplete mechanical remains hinted at additional gear trains, but no previous reconstructions had successfully worked out how all 5 planets could have displayed simultaneously in the limited physical space available. The UCL team's solution was elegant. They proposed a system of concentric rings on the front face, each driven by its own gear train at the appropriate rate to represent the synodic cycles of the corresponding planet: Mercury, Venus, Mars, Jupiter and Saturn each had their own ring, nested concentrically around the central Sun and Moon displays, with each ring having a pointer indicating the planet's current position in the zodiac. The whole assembly would have represented a view of the Greek cosmos in miniature, the Earth implied at the center, the Moon closest in, then the Sun, then the 5 planets at their appropriate distances, all moving against the background of the zodiac at their correct relative speeds. The critical insight that made this reconstruction work was the recognition that the gear components could be shared between the trains for different planets. The same physical gear or the same shaft could contribute to the calculations for more than one planet simultaneously. This dramatically reduced the number of additional gears required and allowed the entire planetary display to fit within the physical constraint of the mechanism's case. The sheer gear architecture requires a deep understanding of the mathematical relationships between the different planetary periods. You can only share a gear between 2 trains if the required ratios happen to be compatible, and discovering which ratios are compatible requires exactly the kind of sophisticated arithmetic that the mechanism's designer clearly possessed. The 2024 Glasgow study. The most recent major analytical contribution to our understanding of the Antikythera mechanism came from an unexpected direction. Researchers at the University of Glasgow, who normally spend their time listening for the death cries of black holes. It began as several important developments in Antikythera research have, with Chris Budaselik's Click Spring project. While working to build his replica of the calendar ring, the outer band on the front face of the mechanism punctuated by regularly spaced holes, Budaselik and his collaborators collected precise measurements of the surviving hole positions in the existing fragments and attempted to estimate how many holes the ring had originally contained before it broke and corroded. Their analysis, published in 2020 alongside new X-ray imaging of the calendar ring, suggested the total was somewhere between 347 and 367. That 20-hole range of uncertainty may sound small, but it matters enormously because the number of holes determines what the ring was tracking. 365 holes would correspond to the Egyptian solar year, 12 months of 30 days plus 5 extra, the calendar the mechanism used in its outer ring. 360 holes would divide the ring into degrees, perhaps for angular measurement. 354 holes would correspond to the Greek lunar year, 12 synodic months of approximately 29.5 days each, the calendar Greeks actually used for their religious and civic life. These 3 entirely different functions, and the ring could only have had one of them. Graham Rowan, an astrophysics professor at the University of Glasgow and a member of the LIGO scientific collaboration, encountered Budaselik's data and recognized something. This was a signal extraction problem, and signal extraction from incomplete, noisy, fragmentary data was precisely what he did for a living, not with ancient bronze, but with the almost incomprehensibly faint ripples in space-time produced by the mergers of black holes and neutron stars billions of light years away. Gravitational waves, when they reach Earth, produce distortions of space smaller than 1,000th the diameter of a proton. Detecting them requires the most sensitive measuring instrument ever built and statistical methods powerful enough to find a coherent signal buried in vibration noise from ocean waves, traffic, and seismic activities thousands of miles away. the specific technique that LIGO researchers used, Bayesian statistical inference, and a computational method called Markov chain Monte Carlo, as well as related approach called nested sampling, are designed to take incomplete, uncertain data and extract the most probable underlying reality from it. To find patterns in noise, to infer structure from fragments. It is, when you think about it, an almost poetic description of what every Antikythera researcher has been doing for centuries, finding patterns in corroded fragments, inferring a whole structure from partial remains. Woen and his colleague Joseph Bailey applied two independent versions of these techniques to Budaselic's calendar ring data. They modeled the surviving hole positions as a fragment of a complete ring of unknown radius and unknown total hole counts, and then asked, what total hole count in what ring radius best explains the observed positions? The two methods were applied independently and then compared to check their consistency. The results, published in the Horological Journal in July 2024, receiving a fresh wave of attention from science journalists and researchers in April 2026, were unambiguous to a degree that surprised even the researchers. The calendar ring most likely contained 354 or 355 holes, corresponding to the Greek lunar year, arranged around a ring of radius 77.1 millimeters, with an uncertainty of only about 1/3 of a millimeter in the radius. This count was not merely more probable than 365 or 360, it was hundreds of times more probable. The statistical evidence was decisive. The lunar year interpretation had been favored by some researchers before this study, but favored and hundreds of times more probable are very different epistemic positions. The Glasgow study did not introduce a new hypothesis. It settled a long-running dispute by bringing a level of statistical rigor that previous analyses had lacked, and it did so using tools developed to detect gravitational waves from black hole collisions, a symmetry that the researchers found both amusing and profound. It is a neat symmetry, wrote Professor Rowan, that we adapted techniques we use to study the universe today to understand more about a mechanism that helped people keep track of the heavens nearly 2 millennia ago. He added, with the deadpan wit that seems to come naturally to physicists working on ancient artifact, we hope that our findings, although less supernaturally spectacular than those made by Indiana Jones, will help deepen our understanding of how this remarkable device was made and used by the Greeks. What the 354 hole count implies is significant. It means the calendar ring was not tracking the Egyptian solar calendar as earlier researchers had assumed. It was tracking the Greek lunar year of 12 synodic months. This aligns the mechanism's primary front-phase calendar with the lunar cycle that governed Greek religious and civic life. The same cycle, tracked by the metonic dial on the back of the device. The mechanism was, at its core, a lunar instrument, oriented around the moon in a way that matched the actual lived calendar of its Greek users. The study also revealed something remarkable about the craftsmanship of the calendar ring itself. The holes in the surviving fragments were positioned with extraordinary accuracy, an average radial variation of just 0.028 millimeters per hole. That is approximately the width of a human hair, achieved by hand in bronze 2,000 years ago. This level of precision, the researchers noted, would have required highly accurate measurement techniques and an incredibly steady hand to punch them. The craftsman who made the calendar ring was not just skilled. By modern engineering standards, they were phenomenally skilled. A recent complication. While the Glasgow study was receiving renewed attention in early 2026, another very recent finding was quietly complicating the received picture of the Antikythera mechanism in a different way, and raising a question that nobody had previously thought to ask with such rigor. Given the actual manufacturing quality of the surviving gears, would the mechanism have functioned reliably at all? In April 2025, two engineers at Argentina's National University of Mar del Plata, Esteban Zaghetti and Gustavo Arenas, published a paper presenting a detailed computer simulation of the mechanism's gear train. Their simulation incorporated two factors that earlier analyses had largely glossed over: the triangular tooth profile of the actual gears and the small but real manufacturing errors present in the surviving fragments. The triangular teeth are a well-known feature of the mechanism. Every researcher who has studied it has noted that the gear teeth are equilateral triangles rather than the involute curves preferred in modern gearing. Most analyses treated this as a minor detail, assuming the gears would mesh smoothly enough for practical purposes. Zaghetti and Arenas took a harder look. Triangular teeth, they found, do not produce uniform rotation during tooth contact. As each tooth engages and disengages, the driven gear briefly speeds up and slows down, a non-uniform motion that involute teeth are specifically designed to avoid. This variation makes every pointer in the mechanism wobble around its intended position, even when the crank is turned steadily. For rough indication, this might not matter much. For precise astronomical prediction over long periods, it introduces a systematic source of error at every engagement of every gear. The manufacturing errors are potentially more serious. The surviving fragments have spent 2,000 years on the sea floor and are corroded and distorted, making precise measurement of the original gear geometry difficult. But the measurements that are available suggest that the gears, while remarkably consistent given the handmade nature of their manufacture, were not perfect. Gear centers were not always exactly where they should have been. Tooth spacing was not always perfectly uniform. In a single gear pair, these small errors might be tolerable, but the mechanism links many gears into a single train, and in a linked gear train, errors cascade. A slight jam in one pair propagates force through the entire system. One frozen gear pair can halt the whole mechanism. When Zaghetti and Arenas ran their simulation with realistic error levels, the results were sobering. Under the conditions their model assumed, the mechanism would have jammed, gears locking solid, unable to advance. After only about 4 months of forward cranking from a given starting point, most simulated runs ended early, and those that did not jam showed pointers drifting out of sync with their intended position over time. The device on this analysis was not a reliable long-term astronomical calculator, but something considerably more fragile. This is a genuinely interesting finding, and it does not diminish the mechanism so much as humanize it. It suggests the device required skilled, attentive operation, that it was not something you could set and walk away from, but something that needed tending, resetting, and careful handling. It also raises the possibility that the device was used primarily as a demonstration and teaching instrument, rather than as a working daily use calculator. Something you would set to a specific date to show where the planet stood, or to find the next eclipse and then reset. This kind of episodic use would have placed far less demand on the mechanism than continuous long-term operation. Researchers have pushed back on the simulation's conclusion, noting that the manufacturing errors in the simulation were derived from corroded, distorted fragments rather than from the original dimensions, and that 2,000 years of saltwater immersion may have warped gear geometry considerably from its original state. A freshly made device running on clean-cut, uncorroded gears might have functioned far more reliably than the simulation suggests. The debate is genuinely open, and the simulation results have not yet been independently replicated. What is valuable about the Argentine study, regardless of whether its specific failure estimates are correct, is the question it asked. It is easy and tempting to treat the Antikythera mechanism as a flawlessly functioning marvel of ancient precision engineering, to let its reputation for sophistication paper over the practical realities of its manufacture. The people who built it were extraordinary craftsmen working at the absolute limits of their technology, with hand tools in an era without standardized measurement, without machine tooling, without the engineering science to calculate gear tolerances systematically. That they produced something this remarkable is staggering. That the result may have had real limitations, that it may have jammed, that it may have required patient-skilled operation, that it may have been more an object of wonder than a workaday instrument, makes it feel more human, more real, more like something people actually made and used and struggled with, rather than a pristine artifact from a more perfect age. Chapter 4. Inside the Machine. The Physical Object Today. The Antikythera mechanism as it exists today is divided into 82 fragments. These are the remnants of what was originally a single device, broken apart either in the shipwreck itself, during the recovery operations, or during subsequent handling and conservation. The three largest fragments, labeled A, B, and C by researchers, contain most of the surviving mechanical and inscriptional content. Fragment A alone contains 27 of the 30 surviving gears. Fragments B, C, and D each contain a single gear. The remaining fragments contain portions of the bronze plates that form the device's outer casing, along with surviving texts of the inscriptions. The fragments are kept at the National Archaeological Museum in Athens, in specially designed display cases under controlled atmospheric conditions, protected from further deterioration by careful conservation. Visitors to the museums can see the original fragments, dark greenish black shape of corroded bronze, alongside modern replicas that show what the mechanism would have looked like when new and what its internal workings would have appeared as during operation. It is a strange experience to see the original fragments after having learned what they contained. They look, as noted, like nothing at all, and yet inside them, preserved in mineral matrix of 2,000 years of corrosion, is one of the most extraordinary objects ever made. the wooden case that originally housed the mechanism has not survived. Wood does not endure for 2 millennia at the bottom of the sea in the way that bronze does, but traces of wood remains on some of the bronze fragments, and the overall dimensions of the device can be reconstructed from the physical extent of the surviving hardware. The box was approximately 34 centimeters tall, 18 centimeters wide, and 9 centimeters deep, a size of a large hardcover dictionary or a moderately thick laptop computer. It was designed to be portable. This was not a fixed installation, not a large astronomical instrument bolted to an observatory floor. It was something you could carry with you, pack into travel chest, take on a ship. The case had a door on the front and a door on the back, each covered with a bronze plate engraved with explanatory text. Both doors could be opened and closed. The outer surfaces of the doors bore the main instructional inscriptions. The interior surfaces of the front and back covers bore additional text. The back plate, the fixed bronze plate that formed the rear wall of the device's interior, had more inscriptions still, particularly around the lower back dial. The total textual coverage was extraordinary for a mechanical instrument. Essentially, every surface that could carry writing did carry writing, all of it functional, all of it explaining how the device worked and what it told you. The main drive gear and crown wheel. A small hand crank, now lost, was attached to the side of the wooden case. This was the device's only external control, the single input that set everything else in motion. The crank was connected via a crown gear, a gear whose teeth are set perpendicular to the gear's face, allowing it to change the direction of rotation from the plane of the crank to the plane of the main gear train, to the large primary gear labeled B1. Gear B1 is the largest surviving gear in the mechanism and the foundational element of the entire gear train. It is a 4-spoke wheel, its 4 arms radiating from a central hub like a simplified wheel with 223 teeth cut around its rim. It is about 13 centimeters in diameter. When the crank is turned, B1 turns. When B1 turns, everything else turns. The number 223 is not arbitrary. It is the number of lunar months in the Saros eclipse cycle, the fundamental eclipse prediction period that the Babylonians had identified and that forms the basis of the lower back dial. By making 223 the tooth count of the primary input gear, the mechanism's designers ensured that one complete rotation of B1 corresponded to one complete Saros cycle, 18 years, 11 days, and approximately 8 hours. Every output of the mechanism is therefore expressed in terms of fractions or multiples of the Saros cycle. The Saros is not just one of the device's outputs. It is woven into the device's very foundations, the heartbeat of its mathematical structure. From B1, the gear train branches outward in multiple directions. The mechanism is not a single linear chain of gears from input to output. It is a complex network in which a single input drives multiple independent outputs simultaneously. This is what allows one turn of the crank to update simultaneously the sun pointer, the moon pointer, the metonic dial, the Saros dial, the games dial, the exalemos dial, and all the planetary displays. The crank turn is a single cause producing many simultaneous effects, like a conductor raising their baton. the pin-in-slot epicyclic mechanism. Of all of the mechanical features of the Antikythera mechanism, the one that most clearly reveals the extraordinary sophistication of its designers is the pin-in-slot epicyclic mechanism used to model the moon's variable speed. The moon does not orbit the Earth in a perfect circle at a constant speed. As Hipparchus had shown, it follows an elliptical path, or rather, in the mathematical framework available to the ancient Greeks, a circle traversed at variable speed, equivalent in its prediction to an ellipse. The moon moves approximately 14% faster at perigee, its closest approach to Earth, than at apogee, its farthest point. This variation is real and observable. The moon's angular velocity across the sky visibly changes over the course of a month, and the difference matters for eclipse prediction because the precise timing and duration of an eclipse depends on the moon's speed at the moment of the eclipse. To model this variation in a mechanical device, to make a gear train produce a smoothly varying output speed rather than a constant one, is a genuine engineering challenge. A standard gear train with a fixed gear ratio produces a strictly constant output speed for any constant input speed. You need something more subtle. The solution the mechanism's designer invented is both brilliant and simple once you see how it works. Two small gears, labeled K1 and K2 by researchers, sit at a particular point in the moon's gear train. Both gears are the same size and have the same number of teeth, 50 each. Under normal circumstances, two identical gears would transmit rotation with a ratio of exactly 1:1, producing no change in speed. But here, the axis of gear K1 is mounted very slightly off-center relative to the axis of gear K2, offset by about 1.1 millimeters. And on the face of K1, there is a small pin that projects perpendicular to the gear's face. This pin engages with a slot cut radially across the face of K2. As K1 rotates, the pin traces a circle, but because the center of that circle, the axis of K1, is offset from the center of the slot's rotation, the axis of K2, the pin does not move uniformly relative to the slot. As the pin moves through the portion of the slot nearest the edge of K2, it pushes K2 faster. As it moves through the portion nearest the center of K2, it pushes K2 slower. The result is that K2 does not rotate at a constant speed, even when K1 does. It speeds up and slows down in a smooth sinusoidal variation, completing one cycle of variation per revolution of K1. This variation is mathematically equivalent to the first-order approximation of Hipparchus's epicyclic model for the moon's anomaly. The angular amplitude of the speed variation, the difference between the maximum and minimum speed, can be adjusted by changing the offset distance between the two gear axes. The mechanism's offset of 1.1 millimeters produces an angular variation of approximately 6.5 degrees, which is reasonably close to the value Hipparchus estimated from eclipse observations. He gave values of 5.9 and 4.5 degrees in different analyses. The difference may reflect measurement uncertainties in the ancient data. To design this mechanism, the mechanism's makers had to understand Hipparchus's lunar theory well enough to translate its mathematical structure into mechanical terms. They had to recognize that an offset axis pin-in-slot connection produces a sinusoidal variation. They had to calculate the correct offset distance to give the right amplitude of variation. They had to fit this mechanism into the available space within the device's case. And they had to manufacture the offset axis with sufficient precision that the mechanism functioned correctly. This is not elementary craftsmanship. This is advanced mechanical engineering, conducted without any of the mathematical or computational tools that modern engineers take for granted. The front face. The front face of the Antikythera Mechanism was a visual representation of the Greek cosmos, a working mechanical model of the sky showing the positions and phases of all observable celestial bodies at any given moment. At the center was a display of the moon, including a small rotating ball, half black, half silver or gold, that showed the moon's current phase. As the moon gear train advanced, this ball rotated to reveal more or less of its illuminated face, mimicking the waxing and waning that a naked eye observer would see in the sky. This is not just a clever trick. It is a visual commitment to something philosophically important. The ancient Greeks had worked out that the moon's phases are caused by its changing geometry relative to the sun and earth. And the phase ball embodies this understanding mechanically, showing the phase as a consequence of the moon's position rather than as an independent phenomenon. Around the central moon display, a sun pointer swept through the zodiac, completing one revolution per year. The moon pointer swept through the zodiac much faster, completing one revolution per synodic month. Both pointers moved against a fixed ring showing the 12 signs of the zodiac, divided into 12 equal 30-degree sectors, the Babylonian equal sign convention rather than the unequal boundaries of the actual constellations. Outside the zodiac ring was a second ring, showing the Egyptian calendar, 12 months of 30 days plus 5 added days for a total of 365 days, which was designed to be rotatable to account for the Egyptian calendar's slow drift relative to the astronomical seasons. The planetary displays, Mercury, Venus, Mars, Jupiter, Saturn, each had their own concentric rings, each driven by its own gear train at the appropriate speed. The innermost was Mercury, the fastest. The outermost Saturn, the slowest. Each ring had a pointer indicating the planet's current zodiacal position. The combined effect of all of these moving rings and pointers would have been a miniature mechanical aurora, a working model of the Greek universe, in which every component moved at precisely the right rate. To set the mechanism to any date and look at the front face was to see the sky as it appeared on that date. The positions of all known celestial bodies laid out against the zodiac, the moon showing its correct phase, the planets occupying their correct signs. The back dials. Where the front face showed the sky as it appeared, the back of the mechanism tracked the great cycles of time through which the sky moved. The back was dominated by 2 large spiral dials, stacked one above the other, each subdivided into cells arranged along the turns of the spiral, each traversed by a moving pointer that indicated the current position within the relevant cycle. The upper back dial was the Metonic dial, tracking the 19-year Metonic cycle in which 235 lunar months equal 19 solar years. The dial was 5-turn spiral, meaning the pointer made 5 complete revolutions over the 19-year period. The spiral track was divided into 235 cells, one for each lunar month, each cell inscribed with the name of the corresponding Greek month. A subsidiary dial within the Metonic dial tracked the 4-year cycle of the Pan-Hellenic Games, the Olympiad dial, whose 4 cells were labeled with the names of the games held each year. The Pythian Games in year 1, the Isthmian and Nemean Games in year 2 and 4, and the Great Olympic Games in year 3. This game dials is one of the most humanly evocative features of the mechanism, a reminder that the device was not just for abstract astronomical calculation, but for navigation of the lived social world, for knowing when the great festivals would be held, when athletes and pilgrims and traders would converge on Olympia or Delphi. The lower back dial was the Saros dial, tracking the 18-year eclipse prediction cycle. It was a 4-turn spiral divided into 223 cells, one for each lunar month. Each cell contained information about whether an eclipse was expected in that month, and if so, what type. The glyphs in the eclipse cells are abbreviated Greek, H for Helios, solar eclipse, S for Selene, lunar eclipse, sometimes accompanied by a numeral indicating the predicted hour of the eclipse, and occasionally a letter indicating predicted magnitude or color. Some cells are blank, no eclipse expected. The pattern of eclipse cells around the Saros spiral encodes the Babylonian eclipse prediction data with remarkable fidelity. The sequence of solar and lunar eclipse possibilities in the mechanism Saros dial matches the pattern expected from the astronomical data to a degree that confirms the device was carefully calibrated to real celestial mechanics. Below the Saros dial was a smaller subsidiary dial, the Exelegmos dial. The dial addresses a subtle problem in eclipse prediction. The Saros cycle of 223 months is not a whole number of days. It is 6,585.32 days, meaning that successive Saros repetition of an eclipse shift in time by approximately 8 hours. After one Saros, an eclipse occurs 8 hours later in the day than its predecessor. After 2 Saroses, 16 hours later. After 3 Saroses, 1 exelegmos of 54 years. The 3 shifts of 8 hours sums to 24 hours, and eclipses return to approximately the same time of day. The exelegmos tile has 3 cells labeled 0, 8, and 16, indicating the accumulated time correction for successive Saros periods. To use the eclipse prediction dial correctly, you had to know how many Saroses had elapsed since the mechanism was calibrated, and add the appropriate number of hours to the predicted eclipse time. The exelegmos dial made this correction simple and automatic. The parapegma. Running in 2 bands across the front face of the mechanism, above and below the main dial, was a parapegma, an ancient Greek star calendar. The parapegma was an inscription listing for each month of the year, the dates on which specific bright star rose or set at sunrise or sunset, as seen from the mechanism's calibration latitude. The rising and setting of specific stars were among the most important seasonal markers in the ancient world. Long before mechanical calendars, before printed almanacs, before smartphone apps, people navigated the agricultural and maritime year by watching when certain stars appeared or disappeared at twilight. The heliacal rising of the Pleiades, their first appearance above the eastern horizon just before dawn after months of invisibility, announced the beginning of the sailing season. The acronical rising of Arcturus, its appearance above the eastern horizon at sunset, warned of the autumn storms. The setting of the Pleiades in the evening marked the time to harvest. The winter solstice could be fixed by noting when the sun rose and set at its southernmost points in the horizon. The parapegma on the Antikythera Mechanism is not merely a decorative feature. It is a practical almanac, telling the device's user what they would see in the sky on any given day, which stars were rising and setting, which constellations were prominent, what the seasonal character of the sky was. Combined with the position of the sun, moon, and planets shown on the main dial, the parapegma gave a complete picture of the sky's appearance at any moment. The specific content of the mechanism's parapegma is closely related to star calendars preserved in the astronomical literature of the 1st century BCE, particularly Geminus of Rhodes, whose isagogy includes a star calendar showing remarkable overlap with the mechanism's parapegma. This overlap is one of the most important pieces of evidence connecting the mechanism to the intellectual tradition of Rhodes. It suggests not just that the device was made there, but it was made within a specific community of scholars whose astronomical literature we can partially read. Chapter 5. Who built it and why? The question of authorship. The Antikythera Mechanism is anonymous. No maker's name is inscribed anywhere on it. No ancient author refers to it by name or describes its construction. We do not know who designed it, who built it, who commissioned it, who owned it, or whose hand last turned its crank before the storm that sank the ship. These are questions that archaeology and analysis may never definitively answer. And yet, the question of authorship is not merely biographical curiosity. The mechanism's authorship tells us about the intellectual tradition that produced it, the community of knowledge in which it was embedded, the chain of human effort and creativity that connected Babylonian tablet scribes to Greek geometers to Rhodian craftsmen to whatever Romans hold it was sitting in when the ship went down. Following the thread of authorship means following the thread of civilization itself. Archimedes. The most frequently proposed candidate for the original designer, or at least the intellectual ancestor of the design tradition that produced the mechanism, is Archimedes of Syracuse. And the case for his involvement, while circumstantial, is not weak. Archimedes, circa 287 to 212 BCE, was the greatest mathematician and engineer of antiquity by almost any measure. He was born in Syracuse, a Corinthian colony on the island of Sicily, and spent most of his life there, maintaining connections with the intellectual life of Alexandria, and probably visiting there as a young man. His mathematical achievements, the calculation of pi to high precision, the proof that the area of a circle equals the area of a right triangle with legs equal to the radius and circumference, the work on spirals that anticipated integral calculus, the systematic development of the lever in the law of the lever, the hydrostatics of floating bodies. These achievements would be remarkable in any era. In the 3rd century BCE, they were almost incomprehensible. Archimedes also had a documented interest in mechanical models of the heavens. The Roman writer Cicero, in his work De Re Publica, describes having seen 2 devices attributed to Archimedes, both taken from Syracuse by the Roman general Marcellus, when he sacked the city in 212 BCE. One was a star globe, a sphere on which the position of the constellations were marked, which could be rotated to show the sky at any hour. The other was something more impressive, a device that Cicero says reproduced the motion of the sun, moon, and 5 planets simultaneously. He described it with genuine wonder. He said that when you turned the device, you could see the moon rise and set in proportion to the sun, and the planets moved at different speeds, and the eclipses occurred at the right times. Cicero drew an explicitly philosophical conclusion. Such an ordered system could only have been designed by a rational intelligence, just as the cosmos itself must have been. Tony Freeth, the mathematician and filmmaker who has led much of the modern research on the mechanism, wrote with characteristic directness, "I personally think it is likely that the original design came from Archimedes, and he started the tradition of making these devices. The Antikythera Mechanism is simply a later version of the Archimedes design, but there is little hard evidence." This is a considered judgment by a leading expert, and it is worth taking seriously precisely because of Freeth's usual rigor. He is not speculating casually. He is making a reasoned assessment on the basis of a careful reading of the evidence, while honestly acknowledging its limitations. If Archimedes did design the original, then the Antikythera Mechanism is a later copy or descendant of that design, updated with newer astronomical data. The Hipparchus-era observation of the moon's variable speed, the Babylonian period relations for the planets as understood in the 1st century BCE, the craftsmen who made the Antikythera Mechanism may have been working from Archimedes' original design, adapting and improving it as new astronomical knowledge became available. This would explain why the mechanism seems to incorporate knowledge that postdates Archimedes while also clearly belonging to a tradition of mechanical astronomy that Cicero associates with him. Hipparchus. If Archimedes is the possible origin of the tradition, Hipparchus is the source of the specific astronomical content. We have already discussed his lunar theory and its direct embodiment in the pin and slot mechanism, but his broader influence on the mechanism extends further. The mechanism's eclipse prediction is based on the Babylonian sorrow cycle, but its implementation reflects the understanding of eclipse conditions that was formalized in Greek astronomical thinking by the time of Hipparchus and his contemporaries. The eclipse cells in the Saros dial include information about eclipse magnitude and timing that goes beyond a simple list of Saros dates. It reflects the additional astronomical insight needed to distinguish probable from certain eclipses and to estimate the time of day. This level of eclipse prediction expertise is consistent with Hipparchian astronomy. The Parapegma's star calendar data has been analyzed and shown to be consistent with observations made from Rhodes at around the time Hipparchus was working there. The moon's anomaly parameter in the pin and slot mechanism, the 1.1 millimeter offset that produces the observed 6.5 degree angular variation, is within range of the values Hipparchus himself estimated from eclipse data, as reported by Ptolemy. The overall mathematical sophistication of the device, its use of period relations accurate to 4 or 5 significant figures, its implementation of epicyclic theory in 3 dimensions, corresponds to the state of Greek astronomy at or just after the time of Hipparchus. Whether Hipparchus personally participated in the design of the mechanism, whether he supervised craftsmen who built it, or whether the mechanism was designed by someone working from his written texts after his death, all remain possible. What seems almost certain is that whoever designed the mechanism had access to Hipparchus's work, understood it deeply, and had the mathematical sophistication to translate it into mechanical form. The craftsman. All the astronomy and mathematics in the world would have produced nothing without craftsmen capable of realizing it in metal. And those craftsmen, whoever they were, deserve far more recognition than they typically receive in accounts of the Antikythera Mechanism. Making the mechanism required an extraordinary combination of skills. The designer, who may or may not have been the same person as the craftsman, had to understand the astronomy deeply enough to know what gear ratios were needed. The craftsman had to translate those ratios into actual tooth count, choosing numbers that were both mathematically correct and physically realizable. They had to draw out the geometry of each gear, the pitch circle diameter, the tooth spacing, the tooth profile, and then actually cut the teeth into bronze with hand tools, achieving sufficient precision and consistency that all the gears meshed properly. They had to drill axle holes, fabricate spindles and bearings, fit everything into the constrained geometry of the wooden case, and engraved thousands of characters of text on the bronze plate. An illegible, consistent script at a scale barely readable without magnification. The YouTube channel Cookspring, run by Australian machinist Chris Budaselic, has documented a remarkable multi-year project to recreate the Antikythera Mechanism using only tools and techniques that would have been available in ancient Greek. The project is ongoing and has become an important source of insight for academic researchers. Budaselic's careful work on the calendar ring, for instance, provided the raw data that the Glasgow gravitational wave researchers used for their statistical analysis. Watching Budaselic work, the careful scribing of geometry, the patient filing and testing of gear teeth, the iterative fitting and refitting of components, gives a visceral sense of both the difficulty and the beauty of the ancient craftsman's achievement. Purpose and use. The question of what the Antikythera Mechanism was used for has surface answer and several deeper ones. The surface answer is that it was an astronomical calculator, a device for determining the positions of the sun, moon, and planets on any given day, predicting eclipses, and tracking calendrical cycles. This is correct but incomplete. A deeper answer comes from looking at who would have used it and in what context. The inscriptions are written in a literary dialect of Greek that presupposes an educated reader, but not necessarily an expert astronomer. The explanatory text is detailed and clear, like a good instruction manual. It does not assume that the reader already knows how the device works. This suggests the mechanism was designed not for professional astronomers, but for educated lay people, wealthy patrons, philosophers, teachers, perhaps military commanders or political figures who wanted access to astronomical information without wanting to master the underlying mathematics themselves. The inclusion of the games dial is particularly illuminating. The Olympic Games and the other Panhellenic festivals were not just sporting events. They were among the most important occasions in Greek civic and religious life. They were occasions for political negotiation, for religious observance, for the affirmation of shared Greek identity across the many city-states and colonies that made up the Greek world. The 4-year Olympiad cycle was one of the primary ways that Greeks of different cities and regions synchronized their activities and tracked time on a shared basis. A device that tracked the game cycle was a device for navigating the Greek social world, for knowing when the great gatherings would occur, when truces would be required, when athletes and merchants and diplomats would be on the road. Eclipse prediction, too, had deep practical and psychological significance beyond pure astronomy. Eclipses were widely understood in antiquity as omens, signs from the gods about the course of human affairs. The ability to predict an eclipse in advance transformed a potentially terrifying omen into an anticipated event. A commander who knew that a lunar eclipse would occur on a particular night could prepare his troops for it, perhaps even turn it to his rhetoric advantage. The Athenian general Nicias, who notoriously refused to move his fleet during the disastrous Sicilian expedition because of a lunar eclipse, might have fared better with access to a device that told him the eclipse was coming. The general who could say, "There will be an eclipse in 3 days, and it signifies our victory because I predicted it," was in a very different position from the general who watched helplessly as his terrified soldiers read calamity in the darkening moon. The mechanism also served almost certainly as an educational tool and a philosophical object. It made the abstract mathematics of astronomy concrete and visible. It demonstrated that the motions of the heavens follow precise mathematical rules, that the universe is orderly, predictable, governed by ratios that can be expressed in gears and dials. For a Stoic philosopher like Posidonius, who had held that the cosmos was rational and ordered, governed by divine reason, a device like this was not just useful, but theologically resonant. It was a small proof of the cosmos' rationality, a bronze argument for the logos that the Stoics believed pervaded the universe. Chapter 6. The 1400-Year Gap. One of the most haunting and philosophically troubling aspects of the Antikythera Mechanism is what came after it, or more precisely, what did not come after it. The mechanism was built sometime in the 2nd or 1st century BCE. The next mechanical device of comparable complexity to appear in the historical record is the astronomical clock of Richard of Wallingford, built at St. Alban Abbey in England around 1330 CE. Between these two objects lie a gap of roughly 1400 years, more than a millennium of silence, in which nothing approaching the mechanism's level of mechanical complexity appears anywhere in the historical or archaeological record. 1400 years, more time than separates Richard of Wallingford from us, more time than separates the fall of Rome from the present day, a gap so vast that it contains the entire Middle Ages, the entire history of Islam through its golden age and beyond, the Vikings and the Normans and the Crusades and the Black Death and the beginning of the Renaissance. All of it fits inside the gap between the Antikythera Mechanism and the next machine of comparable sophistication. How is this possible? How could a technology of this caliber appear, exist for some period of time, and then simply vanish without a trace? The most straightforward explanation is that the mechanism was not quite as unique as the archaeological record makes it appear. We know from literary sources that mechanical models of the heavens existed beyond the single example recovered from the Antikythera wreck. Cicero describes one, as we have seen. Other Roman writers refer to bronze spheres that moved to show the stars and planets. Pappos of Alexandria, writing in the 4th century CE, refers to a work by Archimedes on sphere making, which apparently described the construction of such devices, a work that no longer survives. If even 20 or 30 such devices had been made over the course of the 2 centuries between the mechanism's construction and the end of the Roman Republic, and all of them were eventually recycled, melted down for their bronze, which was a valuable material never wasted when it could be reused, then the archaeological record would look exactly as it does, empty of physical evidence, with only fragmentary literary references as traces. Bronze recycling in the ancient world was systematic and thorough. The great bronze statues that once adorned every Greek and Roman city have almost entirely vanished, not because they were hidden or lost, but because they were melted down. The Antikythera Mechanism survived only because it went to the bottom of the sea before anyone had the chance to melt it down, and because the seafloor preserved it well enough to leave a recognizable relic 2,000 years later. The same mechanism, if it had been in a library or a workshop, would almost certainly be gone today, not a corroded remnant, but completely gone, its bronze reincarnated into something else centuries ago. The political and cultural disruption of the late Hellenistic and early Roman imperial period are the second major factor. Consider what happened to the intellectual world that produced the mechanism. Corinth was destroyed by Rome in 146 BCE. The Library of Alexandria, the greatest repository of ancient knowledge, suffered a series of catastrophic events across several centuries: fire, deliberate destruction, neglect, that progressively reduced its holding. The sack of Athens by Sulla in 86 BCE destroyed much of the city's intellectual infrastructure. The civil wars of the late Republic disrupted trade and travel across the Mediterranean, isolating intellectual communities that had depended on easy communication. The transition from the cosmopolitan Hellenistic world to the Roman imperial world brought with it a shift in cultural values, a decreased emphasis on theoretical natural science, a redirection of intellectual energy toward rhetoric, law, and administration. The tradition of precision mechanical astronomy was a highly specialized craft, dependent on particular skilled craftsmen who had to be trained by master craftsmen, who had been trained by their masters in a chain of transmission that could be broken by war, poverty, plague, or simply the failure to find a successor. A craft tradition is more fragile than a mathematical theorem. A theorem can be preserved in a text and recovered by anyone who can read the text, but a craft tradition requires not just the knowledge of what to do with the embodied skill to do it, built up through years of practice. If the craftsman who knew how to make the precision bronze gear died without training a successor, the tradition was gone. There is a harder, more uncomfortable factor that historians of science take seriously: the active suppression of philosophical and scientific knowledge by the emerging Christian church in the later Roman Empire. This is not a simple story of bigoted clerics burning books, though some of that did happen. It is a more complex story of cultural transformation, in which the institutions that had supported Hellenistic science, The philosophical schools, the great libraries, the patronage networks of wealthy intellectuals were gradually dismantled, marginalized, or replaced by institutions with different values and different priorities. The Neoplatonic Academy in Athens, the last direct institutional heir of Plato's original academy, was closed by the Emperor Justinian in 529 CE. Hypatia of Alexandria, a philosopher, mathematician, and astronomer who was the most prominent intellectual in Alexandria at the turn of the 5th century, and who taught Neoplatonic philosophy and the mathematics and astronomy of the Greek tradition, was murdered by a Christian mob in 415 CE. The event is recorded in detail by several ancient sources and is widely regarded by historians as symbolically significant, the violent end of the last major figure working in the classical Greek intellectual tradition in Egypt. Much of what we know about ancient Greek mathematics and astronomy we know only because of the Islamic Golden Age, the period from roughly the 8th to the 18th century CE, during which Muslim scholars translated, preserved, and extended the Greek scientific tradition. Scholars in Baghdad, Cordoba, Cairo, and Samarkand translated the surviving works of Euclid, Archimedes, Apollonius, Hipparchus, and Ptolemy into Arabic, and in doing so, preserved texts that would otherwise have been lost entirely. When European scholars of the 12th and 13th centuries began the great project of recovering ancient knowledge, they did so largely through Arabic intermediaries, Latin translations of Arabic translations of Greek originals, filtered through 2 layers of cultural transmission. What this means for the Antikythera mechanism is significant. The mathematical knowledge needed to design it, the period relations, the epicyclic theory, the principle of gear design, was in principle recoverable from the surviving texts. But the craft knowledge needed to build it, the specific techniques for cutting small bronze gear to precise tooth counts, the particular skill of miniature instrument making at the required scale, was almost certainly not written down anywhere. It lived in hands, not in text, and when the hands stopped working, the knowledge died with them. The 1400-year gap is not a mystery that requires a dramatic explanation. No alien intervention, no secret destruction of advanced technology by dark forces, though such ideas are entertaining. It is the straightforward result of a sophisticated craft tradition being interrupted by political disruption, cultural transformation, and the fragility inherent in all forms of knowledge that live in practice rather than in text. What is surprising is not that the tradition was lost, but that it existed at all. That for a few centuries in the ancient Mediterranean, a small number of extraordinarily skilled people figured out how to hold the cosmos in a box. Chapter 7. The Fringes of the Map. And now we arrive at the part of the map where the old cartographers used to write, "Here be dragons," or depending on your disposition, the most interesting part of the whole story. Because the Antikythera mechanism does not just raise questions that scholarly research is slowly answering, it raises questions that are, in a deeper sense, unanswerable. Questions about the nature of history itself, about what we know and how we know it, about the strange and somewhat humbling possibility that the ancient world was far more extraordinary than our standard account suggests. These are not scientific questions in the strict sense. They are philosophical ones, and they deserve to be taken seriously, or at least taken slowly in the contemplative way that all genuinely interesting ideas deserves to be taken, not with the reflexive dismissal of the credulous toward the skeptics, and not with the reflexive ridicule of the skeptics toward the credulous, but the genuine curiosity and an honest willingness to follow through wherever it goes. The ancient alien question. Let us begin with the most famous fringe idea associated with the Antikythera Mechanism, and give it the fair hearing it rarely receives. Erich von Däniken, the Swiss author whose 1968 book, Chariot of the Gods, launched the modern ancient alien movement, cited the Antikythera Mechanism as evidence of extraterrestrial interference in human history. The argument in its basic form was that the device was too sophisticated to have been made by ancient humans, that the gap between what we knew ancient Greek technology could do and what the mechanism actually did was simply too large to be explained without invoking assistance from beings of a higher technological order. Beings from another world, he suggested, had either given the Greeks this technology directly or had in some other way intervened in human technological development. Mainstream scholars dismissed von Däniken comprehensively, and on the specific facts of the mechanism, the dismissal is well-founded. We now understand the device well enough, its gear ratios, its inscriptions, its astronomical content, its connections to Hipparchus and the Babylonian tradition, to trace its intellectual genealogy in considerable detail. There's no mysterious gap that requires extraterrestrial explanation. The mechanism is astonishing, but it is astonishing in a way that makes complete sense given what we know about the intellectual world of 2nd century BCE Greece and Rhodes. The knowledge needed to design it was available. The craft skills needed to build it were, while extraordinary, demonstrably achievable with ancient tools and techniques. The mechanism did not come from nowhere. It came from a specific intellectual and craft tradition that we can partially reconstruct. And yet, here is where the dismissal becomes less satisfying. Von Däniken was responding to something real. He encountered the Antikythera Mechanism in an era before the full modern analysis, before the CT scans, and the decoded inscriptions, before the UCL reconstruction. In that earlier context, the device did appear to come out of nowhere. It appeared to have no known precursor and no successor. It appeared to violate the expected trajectory of ancient technology in a way that genuinely seemed to demand explanation. The ancient alien's answer was wrong, but the underlying observation, something astonishing exists here that does not fit our standard picture, was exactly right. And the question that observation generated, where did this come from, was precisely the right question to ask and remains only partially answered. There is something intellectually generous about acknowledging this. The best fringe ideas are often wrong answers to the right questions. The wrong answer can be discarded, but the question deserves to survive, to be taken seriously and pursued rigorously. Von Däniken's question, stripped of its extraterrestrial framing, becomes, was the ancient world capable of far more sophisticated technology than we have assumed? And the answer to that question, as the Antikythera Mechanism itself demonstrates, is yes, but not because of aliens. The Indiana Jones franchise brought the mechanism to a new mass audience with Indiana Jones and the Dial of Destiny in 2023, in which it is reimagined as a temporal navigation device built by Archimedes himself, capable of detecting fissures in time that allow travel to the past. A former Nazi scientist pursues it as a means of traveling back to change the outcome of World War II. The film is entirely fictional, of course, and takes enormous liberties with both the mechanism's function and its historical context. A key plot point involving continental drift, for instance, would not have been an issue for the actual ancient device. But the film reflects in its popular way the same deep instinct that runs through all the fringe theories, the sense that this object is so extraordinary that it must mean something beyond itself, that it must be a portal to something larger, older, more mysterious than the scholarly records allow. The lost civilization hypothesis. Closely related to the ancient alien idea, but in some ways more philosophically coherent and more difficult to dismiss, is the lost civilization hypothesis. This is the suggestion, associated in its most public contemporary form with the writer Graham Hancock, but with a long intellectual history going back to Plato's account of Atlantis and beyond, that human civilization is considerably older and more sophisticated than mainstream archaeology accepts, in that a technologically advanced civilization existed in the deep past, was destroyed by some catastrophe, and left traces of its knowledge in the myths, monuments, and artifacts of later cultures. On this reading, the Antikythera Mechanism is not purely the product of Hellenistic Greek science, spontaneously achieved a level of sophistication far beyond anything else we can document. Instead, it is a relic or descendant of knowledge from a much older tradition, a sophisticated understanding of astronomy and mechanical engineering that the Greeks inherited rather than invented, perhaps through transmission chains that do not survive in the record, perhaps through contact with remnants of lost civilization, perhaps through the gradual recovery of knowledge embedded in ancient religion or mythical traditions. Professional archaeologists and historians are largely skeptical of the specific claim of a pre-Ice Age technological civilization. The physical evidence for such a civilization simply does not exist at the level of detail it would need to. Advanced metalworking leaves chemical traces in sediment. Large-scale agriculture alters the landscape. Sophisticated construction requires quarrying and transport that leaves geological and botanical evidence. The absence of such evidence across the relevant time periods is not just a gap in the record. It is a positive indicator that no such civilization existed. But there is a softer, more defensible version of the same basic intuition that is worth taking seriously. We know, as established fact, that the Antikythera Mechanism incorporates Babylonian observational data going back centuries before the Greeks encountered it. We know that Greek science built extensively on Egyptian, Mesopotamian, Persian, and probably Indian mathematical and astronomical knowledge. We know that the ancient world was more connected, more cosmopolitan, and more intellectually sophisticated than the history textbooks of even a generation ago acknowledged. We know that the vast majority of ancient writing has not survived. The Library of Alexandria's hundreds of thousands of scrolls are gone. The contents of other ancient libraries are largely gone. The oral traditions of non-literate cultures are largely irrecoverable. We know that entire cities, entire civilizations, have vanished without leaving recognizable traces. In this milder sense, in the sense that we know about the past as only a fragment of what happened, and that the tradition that produced the Antikythera mechanism had roots going back much further and running much deeper than the surviving records allows us to see. The lost civilization idea is not a fringe theory at all. It is simply a recognition of the incompleteness of the archaeological and literary record. The Antikythera mechanism did not appear out of thin air. It was the product of a tradition. In the full extent of that tradition, how old it was, how far it reached, what it knew that we do not, is genuinely unknown. The many more were made hypothesis. Here is a theory that sits much closer to the scientific mainstream while still carrying genuinely radical implications. The Antikythera mechanism was not unique. On this view, the mechanism is not a singular wonder, a once-in-a-civilization masterpiece produced by some improbable convergence of genius. It was instead one of many such devices, perhaps dozens, perhaps hundreds, that were made and used throughout the Hellenistic world and the early Roman Empire. Most of these devices were eventually destroyed, melted down for their bronze, or simply lost without leaving any physical trace. The Antikythera mechanism survived only because of its accidental preservation on the sea floor. The literary evidence supports this view. Cicero described Posidonius's device. The Roman writer Ovid refers to moving bronze spheres representing the cosmos. Pappos of Alexandria refers to Archimedes' work on sphere making. Other ancient writers mention similar instruments in passing without apparent astonishment, suggesting these were known and recognized objects, not impossibly exotic rarities. If the mechanism were truly unique, one of a kind, unprecedented in its time, you would expect ancient writers who knew of it to remark on its uniqueness. Instead, the few ancient references to devices like it treat them matter-of-factly, as interesting objects but not impossible ones. If this hypothesis is correct, then the Antikythera mechanism is not a freak accident of history but a window, partial, distorted, but real, onto an ancient world that was considerably more technologically sophisticated in certain domains than our standard picture suggests. The 1400-year gap between the mechanism and the medieval astronomical clocks is, on this view, partly an artifact of the preservation of bronze objects rather than a true gap in human technological capability. The tradition of precision mechanical astronomy was not a brief, isolated flowering, but a sustained practice that lasted for centuries, one that left no surviving artifacts, but whose existence is attested by literary references, by the internal evidence of the mechanism itself, and by the sheer implausibility of the alternative, which requires us to believe that the most sophisticated mechanical device of the ancient world was also the only such device ever made. This is a hypothesis, not an established fact, but it is a hypothesis taken seriously by leading researchers in the field. Michael Edmonds, one of the core members of the Antikythera Mechanism research project, and one of the most careful and rigorous scholars working on the device, has suggested that the mechanism may represent the tip of a technological iceberg, a visible fragment of a much larger tradition that the historical record has almost entirely obscured. The Archimedes singular genius theory. There is a romantic version of the Antikythera mechanism story in which one man, Archimedes of Syracuse, not only designed the original mechanism, but was essentially the single indispensable cause of the entire tradition. On this reading, the mechanism is not the product of a community of scholars and craftsmen working over generations. It is the product of one impossibly brilliant mind that saw all at once how the cosmos could be captured in gears. This is not quite a fringe theory. It is a position that serious researchers, including Tony Freeth, finds genuinely plausible. But it has a romantic, almost mythological quality that distinguishes it from more prosaic scholarly hypotheses. Archimedes occupies a peculiar position in the history of mathematics. He is not just one great ancient mathematician among several. He is, by the assessment of most mathematical historians, qualitatively different from his contemporaries, operating at a level of abstraction and power that was not matched or exceeded until Newton, nearly 2,000 years later. His method of exhaustion was not just an approximation technique. It was a genuine anticipation of the limiting process at the heart of calculus. His work on centers of gravity was a genuine anticipation of the principle of the integral. His proof that the volume of a sphere is 2/3 the volume of its circumscribing cylinder, which he considered his greatest achievement and asked to be commemorated on his tomb, was a result of such elegant difficulty that it was not re-derived by independent methods until the 17th century. If this man, with his mathematical power, turned his attention to the problem of modeling the cosmos mechanically, and we have multiple ancient sources saying that he did exactly that, then the Antikythera Mechanism, or something like it, is exactly what you would expect him to produce. The pin and slab mechanism for the moon's anomaly is the kind of thing Archimedes might have invented, a simple physical device that embodies a mathematical relationship, using the geometry of the offset circle to approximate the sinusoidal variation that the epicyclic model predicts. There is something beautiful about the possibility that one mind in one workshop in Syracuse or Alexandria, sometimes in the 3rd century BCE, first figured out how to put the cosmos in a box, and that the box eventually found its way through whatever chain of copying and transmission and craft inheritance into the hold of a ship that went down in a storm off the coast of a small Greek island, where it waited 2,000 years for us to find it. It is a beautiful possibility. It may even be true. The deliberate suppression theory. This is perhaps the most politically charged of the alternative theories, and it comes in several versions of varying plausibility. The mildest version is simply a cultural argument. Roman intellectual culture, while deeply indebted to Greek thought, was less hospitable to theoretical nature science than the Hellenistic Greek culture it absorbed. Romans valued rhetoric, law, engineering, military strategy, and practical administration. Theoretical astronomy, the kind of precise, abstract, mathematically demanding work that produced the Antikythera Mechanism, had much less prestige in Rome than it had in Rhodes or Alexandria. Without patronage, without an intellectual community that valued such work, without wealthy and educated clients willing to pay for precision astronomical instruments, the craftsmen who could make such things had no incentive to train successors. The tradition died not from active suppression, but from the cultural indifference, starved of the social oxygen it needed to survive. A stronger version focuses on the early Christian church's relationship with pagan philosophical and scientific knowledge. This is a genuinely complex historical question. It is true that some early Christian writers were explicitly hostile to Greek philosophy and nature science. Tertullian's famous question, "What has Athens to do with Jerusalem?" expressed a view that pagan learning was not just useless, but potentially corrupting to Christian faith. It is true that the philosophical schools of Athens were eventually closed by imperial decree. It is true that libraries were burned, that pagan temples were destroyed, that scholars who continued to work in the Neoplatonic tradition faced increasing hostility. The murder of Hypatia in 415 CE is well documented and clearly targeted at someone specifically because of her role as a teacher of pagan philosophy and mathematics. These are facts, not anti-Christian propaganda. It is also true, however, that the picture is considerably more complicated than a simple narrative of religious oppression of science allows. Many early Christian scholars were enthusiastic students of Greek philosophy. The tradition of Christian natural theology, the attempt to understand God's creation through rational inquiry, provided significant support for scientific investigation, at least in certain forms. The monasteries of the early medieval period preserved and copied manuscripts, including scientific texts that might otherwise have been lost. The Islamic Golden Age, during which Greek science was translated and extended, was itself partly made possible by the preservation work of Christian scholars in the centuries before the Arab conquests. The honest assessment is probably this: the transition from the pagan Hellenistic world to the Christian Roman Empire involved a profound disruption of the specific social and institutional arrangements that had supported the kind of theoretical science represented by the Antikythera Mechanism. This disruption was partly caused by deliberate hostility, partly by cultural transformation, and partly by the straightforward destruction of war and political upheaval. Whatever the exact blend of causes, the result was the same. The tradition ended. And here is the most unsettling implication of this train of thought. The knowledge needed to design the Antikythera Mechanism, the astronomical period relations, the principle of epicyclic theory, the mathematics of gear ratio, is recoverable from surviving texts. Ptolemy's Almagest preserves enough of the underlying astronomy. The mathematical tradition transmitted through Islamic world and recovered in European Renaissance eventually produced the precision clockmaking of the medieval and early modern periods, which is in some ways a rediscovery of the tradition the mechanism represents. But how much more was lost? How many texts? How many craft traditions, how many lines of inquiry were cut off not just by the disruptions we know about, but by disruptions we cannot even reconstruct? The Antikythera Mechanism is the one artifact that gives us a visceral, physical sense of what ancient science was capable of at its best. But it may also be a token of a much larger loss. A lost world of precision ancient technology of which only this one corroded lump has reached us, by the accident of a shipwreck through the patience of the sea. Other out-of-place artifacts. The Antikythera Mechanism is the most famous, but not the only ancient artifact that seems, at first glance, to exceed the technological context that produced it. It is worth lingering on some of its neighbors in this category, not because they are all equally credible or equally well understood, but because they collectively suggest a picture of ancient technology that is more varied, more surprising, and more incompletely understood than the textbook version. Hero of Alexandria's mechanical devices. Hero of Alexandria, working in the 1st century CE, described an astonishing range of mechanical devices, including a steam reaction engine, the aeolipile, a metal sphere mounted on a pivot with nozzles that caused it to spin when the steam escaped, automated theatrical performances powered by falling weights and programmable by the arrangement of rope and peg mechanism, a surveying instrument, the dioptra, of considerable sophistication, vending machines operated by the insertion of a coin, and many more. Hero was not just an inventor. He was a theorist who wrote treatises on pneumatics, mechanics, catoptrics, optics of mirrors, and automata. His works demonstrate that ancient Greek engineers had a sophisticated understanding of many mechanical principles, gearing, pneumatics, simple machines, feedback mechanisms, and that the tradition of precision mechanical design was alive in the 1st century CE, at least in Alexandria. The interesting question is why Hero's steam engine did not lead to an industrial revolution the way Watt's did 17 centuries later. The standard answer, that ancient slave economies had no economic incentive to develop labor-saving mechanical power, is probably correct, but feels somehow unsatisfying when you actually read Hero's description. He understood that steam could do mechanical work. He built a device that demonstrated it, and then nothing. The device became a curiosity. It is one of the great counterfactual temptations of ancient history. The Baghdad Battery. In 1936 and 1938, workers at a site near Baghdad discovered ceramic vessels dated to the Parthian and Sassanid periods, roughly 250 BCE to 650 CE, that contained metal cylinders sealed with asphalt stoppers, through which iron rods had been inserted. An Austrian archaeologist named Wilhelm Koenig proposed in 1938 that these were galvanic cells, primitive batteries capable of generating a small electric current if filled with an acidic solution such as vinegar, wine, or citric acid juice. Subsequent investigations confirmed that such vessels can indeed produce about 1 to 2 volts of electrical current when filled with acidic liquids. The mainstream interpretation is that these vessels were used for storing scrolls, not electricity, and there is indeed a simpler explanation for all the features Koenig identified as battery-like. The absence of any ancient textual reference to electrical phenomena, combined with the complete lack of any other evidence for ancient electrical technology, makes the battery hypothesis quite unlikely. But the minority view has persisted for nearly 90 years, precisely because the alternative is difficult to prove conclusively, and because the vessels do, in laboratory conditions, produce electricity. If you fill them with grape juice, they work. Whether anyone in ancient Mesopotamia or Persia ever filled them with grape juice and attached wires, we genuinely do not know. The Phaistos disc. This fired clay disc, found on Crete and dated to approximately 1700 BCE, is covered on both sides with a spiral sequence of symbols impressed into the clay before firing. The symbols appear to have been made with individual stamps, reusable dies, each representing a single sign, rather than being incised by hand. If this interpretation is correct, it represents the earliest known use of something functionally analogous to movable type, some 3,000 years before Gutenberg. The disk has never been deciphered. Its language and script are unknown, and without additional examples, it may be permanently opaque to translation. Some scholars have questioned whether it is genuine, given both its remarkable nature and the circumstances of its discovery. but its existence, if authentic, implies a level of standardization and replication in the scribal technology of Bronze Age Crete that is not attested anywhere else in the ancient world. The Dendera Light. In the Hathor Temple at Dendera in Egypt, carvings from the Ptolemaic period, roughly 300 to 30 BCE, show what some researchers have interpreted as large glass vessels or bulbs containing serpentine forms that resembled the glowing plasma of a cathode ray tube or arc lamp. Egyptian fringe literature has had considerable fun with these images, arguing that they represent electric lighting in ancient Egypt. The conventional interpretation is that they represent lotus flowers, from which serpents emerge, a common religious symbol in Egyptian iconography. And this explanation fits far better with both the artistic context and the absence of any other evidence for ancient Egyptian electrical technology. But the images are, it must be admitted, rather striking. In the history of Dendera light hypothesis is an interesting case study in how visually compelling evidence can survive rational debunking and continue to exert cultural force. What is interesting about all of these artifacts and the Antikythera mechanism itself is not their individual merits as evidence for or against advanced ancient technology, but what they collectively reveal about our relationship to the past. We are, as a species, deeply invested in the idea that history is a story of progress, that we are smarter, more capable, and more technologically sophisticated than the people who came before us, and that this superiority increases as we go further back in time. The ancient world, on this view, was less advanced than the medieval, which was less advanced than the early modern, which was less advanced than us. The Antikythera mechanism challenges this story in a concrete, undeniable way. It is not ambiguous, like the Baghdad battery. It is not potentially fraudulent, like the Phaistos disc. It is not a misinterpreted religious image, like the Dendera light. It is a bronze gear mechanism of demonstrable mechanical sophistication, found in a datable archaeological context, analyzed by multiple independent research teams using the best available scientific technology. And it is unambiguously, dramatically more sophisticated than anything else in the technological record of its era. It is evidence that our picture of the past is incomplete. It is evidence that human brilliance is not correlated with calendar date. It is evidence that the story of technological progress is more complicated, more interrupted, more characterized by loss and forgetting than the standard narrative allows. It is, in the deepest sense, a reminder that we do not know the past as well as we think we do. The mechanism as a philosophical object. There is one more fringe adjacent idea worth lingering over, one that does not quite fit the category of ancient aliens, lost civilization, or out of artifacts, but in some ways the most interesting of all. The Antikythera mechanism is not just a technological artifact, it is a philosophical argument. By building a machine that reproduces the motion of the heavens, its creators were asserting something about the nature of reality, that the cosmos is, at its core, mechanical, that it runs according to rules, that those rules can be understood, encoded, and replicated, that the difference between the sky above and the bronze device in your hands is one of scale, not of kind. This is a radical claim. It is, in essence, the same claim that underlies all modern natural science. The scientific revolution of the 17th century is often described as the moment when Europeans began to think of nature as a machine. When Newton wrote his Principia and demonstrated that the motions of the planets follow the same mathematical laws as falling apples, when Descartes proposed that animals were automata, when Kepler described the solar system as a celestial machine. This mechanistic turn in natural philosophy is usually dated to the 17th century CE, but the Antikythera mechanism was built in the 2nd or 1st BCE, and whoever built it was already thinking mechanistically about the cosmos. They were not just predicting celestial events using mathematical formulas. They were modeling celestial mechanics using physical gears. They were saying, in the most direct possible way, the sky works like this device. The gears are a metaphor and also a literal truth. To understand the gears is to understand the sky. This is, in the deepest sense, the first scientific statement about the nature of the universe, and it was made in bronze in a wooden box 2,000 years before Newton. The Antikythera mechanism is not just the world's first analog computer. It is the world's first argument that the cosmos is computable, that the universe is a machine, and that machines like this can be built to model it. Whether the ancient Greeks who built it and used it fully understood the implications of this argument, whether they saw themselves as making a philosophical claim about the nature of reality, or simply as building a useful instrument, we cannot know. Perhaps some did and some did not. Perhaps Hipparchus, whose mathematics are embedded in the device, understood it one way, and the wealthy patrons who commissioned it understood it another. And the craftsmen who filed the gear teeth understood it a third way, or not at all. Perhaps this is one of those cases where the artifact understands more than any of its makers. Chapter 8. What the mechanism tells us. The nature of ancient Greek science. The Antikythera mechanism has transformed our understanding of what ancient Greek science and technology were capable of, and the transformation is not subtle. Before its recovery in full analysis, the standard historical account held that ancient Greek science, while intellectually brilliant in its theoretical dimensions, was practically limited, capable of abstract mathematics and philosophical speculation, but not of the precision engineering and applied technology that characterized modern science. The Greeks, on this account, thought deeply but did not build ambitiously. The mechanism demolishes this picture. Here is a precision instrument that requires not just theoretical knowledge, but extraordinary practical skills. The mechanism also reveals something important about the relationship between theory and practice in ancient Greek science. One of the standard claims in the history of science is that the Greeks were handicapped by a disdain for manual work, that their philosophical tradition drew a sharp line between the life of the mind and the life of the hand, relegating craft and engineering to a lower social status, and thereby inhibiting the development of applied science. There is some truth in this. Ancient Greek philosophical literature does sometimes express contempt for manual work, but the Antikythera mechanism is evidence that someone, some craftsman, some community of craftsmen, was willing and able to make the most sophisticated theoretical astronomy of their era and turn it into a working bronze device. Theory and practice were not entirely separate in the ancient Greek world, whatever the philosophers said. The convergence of knowledge and tradition. The mechanism is perhaps the most compelling example in all of ancient history of what happens when different intellectual traditions converge. Babylonian arithmetic, Greek geometry, Rhodian craft, these three streams of knowledge came together in a specific place at a specific historical moment in the hands of specific, if now anonymous people, and produced something that none of them could have produced alone. This is a lesson that echoes through the history of science. The great advances tend to happen not in isolation, but at the intersections, where different traditions meet, where different kinds of knowledge are brought into contact, where a theorist and a craftsman share a workshop and each finds in other something they could not have done alone. The Antikythera Mechanism is a bronze monument to the power of synthesis. Questions that remain. Despite more than a century of research and a remarkable recent acceleration in understanding, many questions about the Antikythera Mechanism remain genuinely open and may remain so permanently. We do not know who designed it. The evidence for Archimedes as the originator of the tradition is suggestive, but not conclusive. The evidence for Hipparchus as the source of the astronomical content is strong, but not decisive as to whether he participated directly. The evidence for Rhodes as the place of manufacture is substantial, but not absolute. We do not know how many such devices existed. The literary references suggest at least a few, but we cannot reconstruct a population of devices from so fragmentary of record. We do not know exactly when it was built. The date estimates range from about 205 BCE to 87 BCE, a span of more than a century, depending on which lines of evidence you weight most heavily. The 2022 analysis by Vulgaris and his colleagues, based on the Saros spiral's eclipse pattern, proposed an initial calibration date of December 23rd, 178 BCE. Other analyses have proposed 205 BCE or 87 BCE. These dates are not simply different answers to the same question. They reflect genuine uncertainty about what date means for a device that may have been built at one time and calibrated at another, and then used over a period of years or decades. We do not know who the device's owner was at the time of the shipwreck. We do not know whether it was in regular use or being transported as a commodity. We do not know what happened to the last person who used it, whether they were on the ship when it sank, or whether they had already received their answer from the mechanism and moved on. These unknowns are not failures of scholarship. They are the natural condition of evidence that is 2,000 years old, fragmentary, and largely silent on the very questions we most want to answer. They are, in some sense, the most honest thing about the Antikythera Mechanism. The reminder that even our best instruments of knowledge can only take us so far, and that beyond the reach of the instrument is the territory where imagination must work. Chapter 9. The object in our hands, the museum, the fragments, and what it feels like to see them. Today, the fragments of the Antikythera Mechanism are housed in the National Archaeological Museum in Athens, in a specially designed display area that represents both the original fragments and a range of modern reconstructions showing what the complete device would have looked like and how it worked. The fragments are held in specially constructed cases under carefully controlled atmospheric conditions, protected from further deterioration. They are among the most carefully conserved objects in any museum in the world. Seeing the original fragments in person is a strange and moving experience. They look at first like nothing much, darkened greenish-brown lumps of corroded metal, pitted and irregular, with none of the visual splendor of the great bronze statues that share the museum's galleries. Fragment A, the largest, is the size of a hand. You can see, if you look carefully, the partial outline of gear teeth, the hint of a structural plate, the remains of an axle hole. But mostly what you see is corrosion, the patient chemistry of 2,000 years on the seafloor doing its slow work. Replicas and reconstruction. The history of Antikythera Mechanism replica is itself a history of progressive understanding, each generation of replica reflecting the state of knowledge at the time of its construction. The earliest serious replica was made by Ioannis Theophanadis in Greece in 1934, based on the limited analysis available at the time. Price and Robert Deriski produced a replica following the 1974 paper, embodying Price's gear analysis. Alan Bromley and Frank Percival built a more detailed replica in Australia in the 1980s. Michael Wright produced the most sophisticated pre-CT replica in the UK, incorporating his discoveries about the front-face planetary displays and the differential gear. Since the 2006 publication of the CT data, several independent researchers and institutions have built new replicas incorporating the improved understanding. The UCL team's 2021 reconstruction was accompanied by an animated video that gave the public its most detailed visual model of what the complete mechanism might have looked like in operation. Tony Freeth himself has been involved in multiple reconstruction projects over the year. Perhaps the most humanly interesting replica project is the Click Spring project, because it takes a different approach entirely. Rather than using modern tools and materials to build a replica of what the mechanism looked like, Budiselik uses tools and techniques consistent with what ancient Greek craftsmen would have had access to: files, gravers, bow drills, geometric dividers, and documents every step of the process on YouTube. The result is not just a replica, but an experiment in experimental archaeology, a practical investigation of how the mechanism might actually have been made, what techniques would have worked, what difficulties ancient craftsmen would have faced, and what solutions they might have found. It is a remarkable project and has contributed genuinely to scholarly understanding, as the 2024 Glasgow study demonstrated. The mechanism in popular culture. The Antikythera mechanism has become one of the touchstones of contemporary popular science culture, an object that appears with regularity in documentaries, science journalism, science fiction, and popular history, always carrying the same freight of wonder and historical provocation. The Indiana Jones franchise brought it to the largest possible audience with The Dial of Destiny in 2023, in which it is reimagined as Archimedes' dial, a device that can detect fissures in time. A Finnish metal band called Nightwish included a track titled Antikythera Mechanism on their 2024 album Yesterwind, and partnered with Finnish watchmaker Puch Watches to produce a limited edition timepiece with design elements referencing the mechanism. A 10x scale replica was inaugurated in Hermosillo, Mexico in February 2024. Google marked the 115th anniversary of the mechanism's identification with a Google Doodle on May 17, 2017. This cultural omnipresence reflects something genuine and not trivial. The mechanism has captured the collective imagination in a way that very few archaeological objects manage to do. It speaks to something deep in the human relationship with time and the cosmos, the desire to understand the heavens, to bring their vast cycles within human grasp, to build something that holds the universe in miniature. It tells us that this desire is ancient, that the impulse to model and calculate and comprehend the sky is not a modern innovation, but a feature of human consciousness as far back as we can see. And it tells us that when the impulse found the right combination of mathematical knowledge and craft skill and material resources, it produced something extraordinary, something that still has the power 2,000 years later to stop people in their tracks and make them feel, however briefly, that they are in the presence of something that exceeds the ordinary scale of human achievement. Conclusion. The ship went down in a storm sometimes around 70 to 60 BCE in the narrow passage between Antikythera and Crete. The storm came up fast, as they do in that part of the Aegean, and the big merchant vessel, overloaded probably with looted art and luxury goods from across the Greek world, could not hold its course. It went down in relatively shallow water, 45 meters, near the rocky eastern cape of the island, and the cargo scattered across the sandy bottom and stayed there in the cold dark for nearly 2,000 years. We do not know what date the mechanism was set to when the ship went down. We do not know whose hands it had last turned the crank, whose eyes had last looked at the face and read the positions of the planets in the zodiac, whose fingers had last traced the spiral cells of the eclipse dial. We know only that someone somewhere in the Hellenistic Greek world had in their hands a device that could hold the cosmos. They could set it to any date, past, present, or future, and see where the sun and moon and planets stood. They could look up the next eclipse, the next Olympic Games, their position in the great 19 cycles of lunation. They could trace the slow machinery of the heavens through the dials of a mechanism small enough to carry under one's arm. The scholars who devoted their careers to understanding this object, Price, Bromley, Wright, Edmonds, Freeth, Jones, and many others, gave us the gift of knowing what it was. The CT scanners and the polynomial texture mapping and the gravitational wave statistics gave us the gift of reading its hidden text. The craftsmen who built it, whose names we do not know and probably never will, gave us the gift of the object itself, and the sea gave us the gift of preservation. 2,000 years of cold salt water doing the slow chemical work of mineralization, encasing the bronze gear in the protective matrix, keeping the inscriptions readable under their crust of corrosion, waiting patiently for the technology and the curiosity to arrive that could read them. The French theorists and the rigorous archaeologists, the Indiana Jones script writers, and the gravitational wave physicists, the YouTube machinists, and the Oxford classicists, all of them are responding to the same thing, the same object, the same awe, the same haunted feeling of standing in front of something that exceeds the world that made it, that opens a window onto a past that was stranger and richer and more extraordinary than we had any right to expect. The Antikythera Mechanism is the oldest analog computer ever built. It is the most sophisticated technological artifact to survive from the ancient world. It is a monument to the power of intellectual synthesis, of Babylonian patience in Greek geometry and Rhodian craft, combined in ways that none of these traditions could have achieved alone. It encodes 2,000 years of astronomical observation in 30 bronze gears. It models the irregular orbit of the moon with a pin in a slot, offset by 1.1 millimeters, with a precision that would not be matched for 1,400 years. It predicts eclipse using a cycle first identified in Mesopotamia, encoded by craftsmen on a Greek island. discovered from the sea by sponge divers from Simi, and understood at last by physicists who also listen for gravitational waves from colliding black holes a billion light years away. And it tells us, perhaps most importantly, that what is lost is not necessarily gone forever. Given enough time, given enough curiosity, even the right technology and the right questions, even 2,000 years of silence can be heard. The darkness of the seafloor is deep and cold, but the gears kept turning in their mineral sleep, waiting. And when we finally found them and opened them and read the tiny Greek letters hidden inside the corrosion, read the mathematical relationships encoded in the tooth counts, read the astronomical cycles written in bronze, what we found inside that lump of ancient metal was this: a mirror, a small bright mirror reflecting back to us our oldest and most persistent instinct, the instinct to look up, to wonder, to reach out towards the stars and try with whatever tools we have to understand them. We look up at the same sky they looked at, felt the same pull, asked the same questions, and found, at the bottom of the sea, the proof that they had too.